Hello friends. So you are probably going to encounter graph questions at some point in your career, for sure in any of the technical interviews. And there is a very clear reason for that. Graphs are one of the most relevant data structures out there. If you see companies such as Twitter, Facebook, Instagram, LinkedIn, they all won't be possible without the graph theory and the graph implementation of the data structure in the real world. So there is a very direct correlation between the theory or the data structure and its implementation. So that's why interviewers love asking this question. And in this video, I have orchestrated a group of 11 most asked graph questions, and I have sorted them based on like easy, then medium, and then hard. So if you do these questions, you would probably get an idea of what all kinds of questions can be asked and how can you tackle them, how can you better prepare for yourself. So good luck with your interviews and hope you find this video useful. So the question is number of provinces. This is a LeetCode 547 problem, and this problem has been popular amongst top tier companies. So companies such as Amazon, Bloomberg, Apple, Two Sigma, DoorDash, Goldman Sachs, Google, Uber, they have all asked this problem. So that's why I hope that you pay enough attention to this one. If we see the problem statement defines that there are n cities that we are given, and we are told that some of these cities are connected, some of these cities are not connected. Now if say city A is connected with city B and city B is directly connected with city C, then city A is indirectly connected with city C. So A is connected with B is connected with C. Suppose this is the relationship, then we can define that A is also connected with C. This is what this problem is, the statement is referring to. Now going back, we are given the definition that what a province is. A province is a group of directly or indirectly connected cities and no other cities outside of this group. So suppose we are given cities like A, B, C, D, something like this. And we are given that A is connected with B, B is connected with C, and we can also refer that indirectly A is connected with C as well. Currently this D is not connected with anyone. In this case, we can define that this A, B, C makes a province, and this D by itself, currently since it is not connected, it is not making a province. But suppose we identify that another city E that exists that is connected with city D, then we can define this to be the second province as well. Okay, so now we know that what the problem statement has given us. We are given n cities and we are given the connection between those cities, and we are also given the definition of what a province is. Now we are given an n cross n matrix, and wherever there is a connection between any two entities, that particular value has been marked as 1. That defines that the ith city and jth city is connected. And if the value is not 1, if the value is 0, which means that those values are not connected. Now based on this given input, we need to define the total number of provinces. This problem is very similar to one of the previous problems we solved, and that is the number of connected components. And how? Let me just quickly show it to you. What we are given is that we are told that we are given a matrix, and inside the matrix, using the values 0 and 1, we are going to define that whether any two values are connected or not. Okay, so suppose the values are A, B, C, D, and here A, B, C, D. Okay, all the values are by default going to be connected with each other, so I'm going to mark it as 1. Suppose, let's just take the same example. So these are all the items we are given. This is true. Based on all of these items, what we are given is that this is actually not a matrix, but actually this is an adjacency matrix. And adjacency matrix is one more way to represent a graph. Since this is one more way to represent a graph, we can, rather than considering these as cities and these are connection between them, let's just try to think of these as nodes and edges, where nodes are the cities and edges are the connection between them. And now this becomes a very simple problem that we can solve using BFS quite easily. And the whole problem statement now becomes is that we need to identify that how many number of connected component exist inside any given graph, and those connected components we need to return them as the answer. So I have already solved this one in past, but I'm going to quickly show you the solution again. And simply we are going to use breadth first search. For breadth first search, we all know we need two items. First one we need is a queue, and we need some way to keep track of all the visited nodes so far. So let's just do that. I'm going to initialize our queue, and also I'm going to initialize our hash set that is going to keep track of the visited hash set. Okay, so this one is for visited and this one is queue. Now we can start at any given node. So suppose this is the input we are given. Currently nodes are 1, 2, 3. These three cities are connected, and city 4 and 5 is connected. We are also going to mark one more variable called provinces, and initially the value of the provinces is going to be 0. Okay, so currently this is the variable that is going to keep track of the number of provinces we have been able to find so far. Currently the value is 0. Now let's just pick any arbitrary value. So we start with node 1. So let's just run a BFS starting with node number 1. So first we are going to, since 1 has not been visited, we are going to mark as visited because we are visiting it. We are going to add 1 inside our queue. Now the moment we find a value inside a queue, we are going to iterate through its neighbors. Currently 1 has two neighbors, value 2 and value 3. Both value 2 and value 3 are not visited, so we are going to mark them to the number of visited nodes, and we are going to mark 2 and 3 here. Now we iterated over all the neighbors of 1, so we are going to dequeue 1 out, and we are going to remove it from the queue. Now currently we only have values 2 and 3. For value 2, the number of node is 1 and 3 as its neighbor. Both 1 and 3 have been visited, so since they are visited, we are not going to revisit them, and we are going to pop 2 out as well, that stating that we visited all the nodes of 2. And at the same time we are going to pop 3 out as well, since the neighbors of 3, 1 and 2 are already been visited. Also, I forgot one key important thing, and that is that the moment initially when we started iterating through 1 and we found that 1 has a neighbor 2, immediately we needed to add the number of provinces to 1 because we found at least one province. So we would have found one province, and in order to finding that province, we already visited all 3 nodes. So we are going to mark these 3 nodes as visited. Now since in the input we are already given n is equal to 5, we initially started with n is equal to value number 1 because it was not visited. Now we will start with n is equal to 2, but that has also been visited, so we will simply skip over. N is equal to 3 has also been visited, so we will simply skip over. Last value is n is equal to 4. N is equal to 4 has not been visited, so marking 4 to our visited list, adding 4 to our queue, and now 4 has a neighbor 5. So again, the moment we find a neighbor, we are going to increase the number of provinces to 2. We are going to add 5 to our visited list. We are going to add 5 to our queue, and then we are going to pop 4 out because we visited all the neighbors of 4. But we haven't visited all the neighbors of 5. Currently for 5, since 5 has already been visited, we do not care, but 5's neighbor 4 has also been visited, which means 5, we also visited all the neighbors of 5. So now we get rid of 5. Now initially for this n is equal to 5, we had gone through 1 to 4. For the 5th value, 5 is also present inside the number of visited list. So we can define that 5 has also been visited, and because of that, we went through all the nodes or all the cities that we were given, and the number of provinces that we were able to make was 2, and which we are going to return as the answer. If we see solution for the time and space solution for this one, basically the time complexity is going to be big O of v plus e, where v is the number of vertices or number of cities in this case, and e is the number of edges or the connection between the cities that we are given. Pretty simple, and this is pretty standard. Space complexity also going to be big O of v, because the space complexity is based on the visited hash set and the queue that we have to generate, which can hold maximum up to 5 cities for this example. So it is directly related to the number of vertices that is present inside our given example. Awesome. So see how knowing BFS made our life so much easier. Let's move on to the coding explanation for this problem. Let's see the coding solution for the number of provinces problem. This is a really unique problem, and the solution is actually quite simple. First of all, in the main method, we are given the 2 by 2 matrix that defines that what are the number of connected components. Based on that, we would be able to easily identify that what is the total number of edges or total number of nodes present. And once having that, we are going to initialize our visited Boolean array. And initially, the number of provinces is going to be 0. Now, we are going to run our for loop where we are going to call the BFS method. Inside the BFS method, first of all, we are going to check that whether the current node has been visited or not. If the node has not been visited, we are going to call BFS method to visit all the connected components or all the cities that are connected with each other that form a province. And we are going to increase the number of provinces. So we are going to do provinces plus plus, that was initially set it up as 0. Now let's see that what is going to happen inside our BFS helper method. The answer is quite simple. In the BFS, we are going to initialize our queue, and we are going to have a visited array that to keep track of all the nodes that we have visited so far. For any single input that we are given, we are going to keep on iterating all the neighbors of that particular node that it is currently connected to, and we are going to mark all of them visited. So even when we encounter the same city that has already been processed, we do not reprocess it again because it has already been marked visited. And after this entire process ends, currently in this loop, this provinces variable should have all the answers populated. We can simply add them over here and return provinces as the answer. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 99.26% faster. So this is pretty fast solution. And don't worry about this. I'm going to paste this solution inside my GitHub, and the link is in the description, so you can check it out from there. So today we are going to do find the celebrity LeetCode problem, and if we see some of the popular companies, the problem has been asked that companies like Amazon, LinkedIn, Pinterest, Microsoft, Facebook, Apple, Snapchat, Google, Uber and Goldman Sachs. So basically all the popular companies have asked this question. So I'm going to pay my utmost attention. I hope you also enjoy the video. This has to be one of the most interesting problems I have been able to find so far. If you look at this, LeetCode categorized this as a medium problem. If you try to understand the problem statement and try to think about it, you will feel like this is actually a hard problem. And once you put like some more thought into it, you are actually going to feel that this is actually an easy problem. So in my opinion, this is actually an all-in-one problem. Let's understand the problem statement to go further deep. It says that suppose we are at a party with n people, and the names of these people are the numbers. So basically numbers from 0 to n minus 1. So say for an example, we are in a party with 4 people. Basically the people are going to be 0, 1, 2 and 3. So these are going to be the 4 people. Now we are told that in this party there may exist. So this is an important part, that there may exist, which means there might be a celebrity or there might not be a celebrity. Okay. Now we are first of all given that what the definition of a celebrity is. The definition of a celebrity is that that every single person in that party knows who the celebrity is. And the second condition is that celebrity does not know any single person in that party, which is how typical celebrities are. So now given these two definitions, first of all, we are told that we need to check that whether there exists a celebrity or not. And if there exists a celebrity, basically we need to find that who that celebrity is. The question is how we are going to find who that celebrity is. Well, definitely over here the relationship is based on either people knowing who the celebrity is, or the fact that celebrity knows no one, that everyone knows celebrity and celebrity knows no one, right? Now at our advantage, we are given a methodology where we can check between any two entities whether they know each other or not. We have a method boolean knows A to B, which defines that whether A knows B or not. If A knows B, if this gives answer true, which means A knows B. If this gives answer false, which means A does not know B. And why we are using that? Because the only relationship we have to identify whether a person is a celebrity or not is by the amount of people know them or the amount of people they know. And in this case, we either need to find the celebrity or we need to return -1 if no celebrity exists. So I know this is a little bit complicated to understand, but let's try to see some examples for this problem. Okay, so in the problem, we are actually going to have an input that looks like this, where in this input, we are given a list of lists that contains some values that defines the relationship between any two values, that whether they know each other or not. Now, the thing is, this input is kind of messy, so I'm not actually going to show you examples based on this exact input. I'm actually going to show you in the base of something that is easier to visualize. So this is the same input I took from here, but I have actually converted it into a 2D matrix. And basically, as an input, we are given a graph, or we are basically given an adjacency matrix. Okay. So for this adjacency matrix, we based on this adjacency matrix, we are given two entities. We are given a person and we are given whether that person knows each other or not. This diagonal line is always going to be 1 because that defines that whether person 0 knows person 0 or not, whether person 1 knows person 1 or not, things like that. And that is always going to be 1. So we can simply ignore this one. This serves no purpose. The important thing in this case is this defines that whether person 0 knows person 1 or not. So this answer is 1, which means that person 0 knows person 1. Let's try to find who the celebrity is in this problem, right? So in this case, we are given basically 3 person. So we can actually create a graph that looks like this of 3 person, and we are going to name them as 0, 1 and 2, right? Now the thing is, relationship between them is actually going to be the relationship defined by an edge, where a edge would represent that whether one entity knows the other entity or not, or one node knows the other node or not. And this is going to be a directed edge. Why? Because it could be possible that 0 knows 1, but 1 does not know 0. So we cannot just simply have an undirected edge. We must have a directed edge in this case. So let's try to do that as well. So if we draw it from this graph, okay, 0, 0, this does not matter, these three values, so we'll just ignore them. Let's just start 0 with 1. So 0 knows 1, right? So which means 0 knows 1. Yeah, we mark it. Now, does 0 know 2? No, 0 does not know 2. So there is not going to be any edge. Now, whether 1 knows 0? No, 1 does not know 0, and 1 also does not know 2. So 1 does not know anyone. Now in this case, whether 2 knows 0. Yeah, so 2 knows 0. That is good. And whether 2 knows 1. Yeah, 2 also knows 1. So that is also good. And 2 knows 2. Yeah, that is true. So we can ignore that. In this case, if we see the two definitions of a celebrity, that everyone knows who the celebrity is and celebrity knows no one at the party. So definitely in this case, we can say that, hey, if we check out the input for this value number 1, it knows itself. But the thing is, that is not the point. The point is whether it knows anyone else at the party or not. So 1 does not know anyone at the party. That is true. And also 0 knows 1 and 2 also knows 1, which means every single one who is every person other than 1 knows who the 1 is, and 1 does not know anyone, which means 1 perfectly fits on our category of celebrity, and in this case 1 is going to be celebrity. So we will simply return 1 as the answer, and this is what we need to return. Okay, let's see one more example. In this case, again 0, 1 and 2. Let's draw 3 lines. Now ignore these 3 cases, and 0 knows 1. No, 0 knows 2. Yes, so 0 knows 2. Okay, does 1 know 2? Yeah, 1 also knows 2. That's good. Whether 2, okay, 2 knows 0. So in this case, 2 knows 0 and 2 knows 1. No. So in this case, can we find any celebrity? Actually, we cannot find any celebrity. Why? Because in this case, okay, 0 and 1, both of them know 2. So that is good. 2 qualifies for one of the property of being a celebrity. The thing is, second property of being a celebrity is that it has to know no one at the party. But in this case, 2 actually knows who the 0 is. So because 2 know one person, 2 does not qualify for the second entity of our answer. So in this case, we cannot find any celebrity. So because there is no celebrity present, we are simply going to return -1 as the answer. And this is what we need to return. Okay, so first approach is a brute force approach. In the brute force approach, what we are going to do is we are simply going to check that whether all the person that are given, can any single one of them is a celebrity. So for one by one, we are going to check for every single person whether they are celebrity or not. So in this case, what we are going to do is first we will consider person 0. Okay, so for the person 0, we will try to see whether 0 is a celebrity or not. How can 0 be a celebrity? If everyone else knows who the 0 is and 0 knows no one. So in this case we can see that 0 knows someone, so 0 is not a celebrity. Now we will have to check whether 1 is a celebrity or not. So in this case, okay, 1 still knows someone, so 1 cannot be a celebrity, but and in this case we'll try to see whether 2 is a celebrity or not. So 2 knows no one, and let's see that if everyone knows 2 or not. So this one does not knows 2, but this one does not know 2. So 2 is also not a celebrity. So in this case we will return a -1. And this logic leads us to the correct answer. Some maybe if you make some modifications or tweaks, it can be an acceptable solution as well. The thing is, this is still not the most optimal way to solve this problem. So basically we would end up solving this problem in big O of n square time. So which is not too bad for some of the problem, but it is really bad for this problem because this can be done very efficiently with other methods. So let's try to see what that other methods could be. So in this scenario, if we see, okay, 0 knows 1 and 2. So 0 knows 1 and 2, right? Same way, 1 does not know anyone and 2 knows 1 and 1 and 0. So 2 knows 0 and 2 knows 1. So is basically answer is going to be 1. That is a given fact. The thing is, what is one smart trick we can use? The smart trick is the knows function. The knows function that we are given in the input, that is there for a reason. And what knows function does is that if we provide any two values, say for example, if we provide the values of 0 and 1, it is quickly going to tell us that whether 0 knows 1 or not. So in this case, okay, 0 knows 1, that is a true fact. Now the thing is, if we know for sure that 0 knows 1, what is one thing we can say for guarantee? We can say for guarantee or for certainty that 0 cannot be a celebrity. Why we can say that? Because remember the definition of a celebrity. The definition of a celebrity is that everyone knows the celebrity and celebrity knows no one. Which means in this case, if we try to find or if we try to see this knows function between 0 and 1 and the answer is true. If the answer is true, definitely we can say that 0 cannot be a celebrity. Which means we are eliminating 0. Now, what could be the second possibility? Second possibility could be, say for an example, if we try to use the knows function for values 1 and 2. If we try to use the function 1 and 2 knows, the answer is going to be false. Why the answer is going to be false? Because 1 does not know 2. If 1 does not know 2, what is also one more thing we can say for certainty? Well, we can say for certainty that in this case 2 cannot be celebrity. Why 2 cannot be celebrity? Because we found at least one element that does not know 2. And in order for 2 to be celebrity, celebrity has to be known by everybody else in the party. So because we find one entry over here who does not know 2, we can say for sure that 2 is not a celebrity. Which means depending on the result of this knows function, if the value is true, we can eliminate one value, that is the first value in the knows function. If the value is false, we can eliminate the second value inside this given input, which means with every single knows call, we are getting rid of one element. So in this case, after just making two calls, we were able to get rid of 0 and 2, which means if there exists a celebrity, it has to be 1. So now all we need to do is that since this is the last item or last value pending, do we need to check that whether everyone knows 1 or not? No. Why? Because since we know for sure that these two are not the celebrities, right? So all we will have to worry about is that whether 1 knows no one. If 1 knows no one, which means 1 has to be the celebrity. If 1 knows at least one person, which means there are no celebrities inside this input, and we can simply return -1. And this is the whole logic behind this problem. Let me try to explain very quickly with a big example. So now we have a bunch of different values over here. Basically, we are simply going to use the knows function and we are going to go through every single value and try to see whether it knows the next value or not. So first we'll try to see that whether the 0 knows 1 or not. So, and we can ignore all of these values because diagonals doesn't matter. We do not care if they know their own self or not. So in this case, okay, 0 to 1, 0 does not know 1, which means we can say for sure that 1 cannot be celebrity. If 1 cannot be celebrity, we can simply skip over to the second value. Now in this case, we will check that whether 0 knows 2. So in this case, 0 to 2, 0 knows 2. So because 0 knows 2, we can say for sure that 0 cannot be a celebrity. So we ignore this. Now we are at this value number 2. So we'll try to see whether 2 knows 3 or not. So 2 to 3, if we check, okay, 2 knows 3. So if 2 knows 3, definitely 2 cannot be a celebrity. So we will ignore that. Now we are at this value number 3. So we'll check for 3 to 4. So 3 to 4, if we check, yeah, 3 knows 4. So in this case, 3 cannot be a celebrity because 3 knows 4 because of this value. Now we are at this 4 position, number 4 to 5. So if we see 4 to 5, so 4 to 5, this value is actually 0, which means 4 does not know 5. So because 4 does not know 5 cannot be a celebrity. So in this case, we have actually got rid of all of these elements and only fourth value is pending. So now we know that if there exists a celebrity, it has to be 4, otherwise there are no celebrities. So now we are simply going to check that whether 4 knows anyone or not. And for that, we simply have to do one check at this fourth row to see whether apart from 4 by itself, does it know anyone else? And it knows no one. So definitely 4 is the only candidate left and 4 knows no one. So in this case, 4 is definitely our celebrity, and this we can simply return as the answer. And this is the whole logic behind our answer. Say for an example, in this case, by chance, if 4 knew this value number 1, if this was answer 1, then simply we can say that, okay, 4 is also not a celebrity, and we can simply return -1 in this case. The thing is, because this value is actually 0, so in this case, answer is actually going to be 4, and we are solving this problem most efficiently. If we see time complexity in this case, the time complexity is actually going to be big O of n. And if we see space complexity, well, apart from using a couple of variables, we are not using any additional space. So space is actually going to be constant. First, I identify few things. So I created a new global integer to use the number of people, and I have assigned it to the value of n. And basically in the problem, we need to resolve this find celebrity problem. And also for this problem, I have created is celebrity a helper method. So that is going to define that whether any single candidate that we have been able to identify from this find celebrity method, if that is a celebrity or not. And now first let's start implementing this find celebrity method, and then we will implement our is celebrity method. So first of all, we are going to initialize a variable called celebrity candidate. Now we are going to run our for loop, and for every single value we are going to check, or we are going to call our knows function. And for the knows function, we are basically providing the value of the celebrity candidate and the value of current I. Now depending on the answer we get back, we are going to update the value to the I. So what this is going to do is, this is simply going to eliminate every single value for us except one last remaining candidate, and that we are going to consider as the celebrity candidate. And once we get out of the loop, all we will have to do is we will have to call our is celebrity method. If this value is actually true, if this value is a celebrity, we are going to return this. And if that is not the case, we can simply return -1. Now in this method, we will first of all run a for loop. Inside the for loop, first we will have to check that if the given value of I is equal to j, which means we have found a diagonal value. So in this case, we simply ignore that. And if that is not the case, we are going to check that whether j satisfy all the properties of being a celebrity or not. If any of these is true, we can simply return false. And if that is not the case, and if we get out of the loop, we can simply return true. And I think this has to be the whole logic behind this input. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, and it is also really efficient in terms of time complexity. So this was a great problem to solve and to understand a lot of different concepts. I would be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Graph problems have always been a big no-no for me. I have always been afraid of graph problems, but the thing is, now I have decided to take them heads on, and today we are going to start doing more graph videos. So this is the first of many graph problems to come. And this question has been really popular with Facebook recently. It's been asked 44 times, which is a huge number. Also, key other companies like Amazon, Google, Bloomberg, Microsoft, Twitter, they are also asking this question. But the thing is, Facebook for some reason has been really interested. So I highly urge you to go and check this video if Facebook is one of your dream companies to join. Okay, this is a LeetCode medium problem, and we are given a reference node in a connected undirected graph. So first let's understand the meaning of these two values. Suppose we are given a graph like this. Notice that there are only 4 nodes, and from any single node we can reach to all the other nodes in the given graph, which means that this is a connected graph. So this is what connected means. And undirected graph means, suppose we are given a graph like this, and we establish that A is B's neighbor, which means that we can traverse from A to B, and also we can traverse from B to A. So there is no restriction regarding the direction of any edge between two nodes. So we are given a reference point to that, and we need to return a deep copy of the graph. So what does a deep copy of the graph means? That suppose we are given a graph like this, so we need to return a graph like this, where if you see the values of the nodes, they are all the same. But the thing is, we are not using the exact same nodes. We are using different nodes with same node values, which means that this would be a legitimate case where we can consider this as a deep copy of this original input. The thing is, if we create a graph like this, over here we are using the same node to represent over here, which means that we are not creating a copy of this original graph. We are just referencing this point to whatever value we had over here. So this is not what we want to give. And also, if we create some graph like this, if we see the values of the nodes, the values remains the same. But the thing is, the ordering is different, that in terms of neighbor selection and how they are perceived, they are different. So this is also a false case. We need to return a copy of this exact same input, just with the nodes that are copied from this one. So at the beginning, the most basic idea we are going to have is that, okay, we are given an input, we are given a reference point, we know that the input graph is connected, which means that there are no loose ends that we have to worry about. So why don't we just traverse through the given input graph? At every single node, we start creating a copy of it. We start creating the same sort of neighbor connections that we have in the original graph, and then just try to return the new graph. That would be a perfectly good logical rational person would think, and that would be a good entry point to start our solution. But the thing is, we are going to see that with that approach, what would be the issue, how can we remediate that issue, and what would be the final solution. So let's start. So first of all, suppose in this given input we start at this one position, so we create a new node 1. Okay, now from this one we can go to any neighbor, we can go to 2 or we can go to 4. Let's say that we go clockwise, so we go to 2. So we create a new neighbor over here called 2. Again from this 2 we go to 3, and over here, keeping the same logic, we create a new node. Now notice one thing, that initially we created a clone over here, we went to its neighbor. Again we created a clone over here, we went to its neighbor. Again we created a clone over here, we will go to its neighbor. So basically we are doing the same problem again and again for different kinds of input. So that should immediately click in your mind that this we are going to solve recursively. So just keep this in mind, that this is a very good way to use the recursive approach. And now at this 3, again we go to its neighbor. So we'll create an edge and we'll create a new node 4 for this one. So from this 4, again we go to its neighbor. Again we go over here. But the issue with this approach is that for this our recursion to end, we need to have a terminating case. But in this scenario, we are not terminating it anyhow, because the thing is, the graph is connected. We are terminating in a scenario where if the graph is empty, we return something empty or something like that. But the thing is, over here again, when we come back to this one, we are still going to see that, okay, this is 1, we need to create the clone of it. We will create a clone of it again over here, which means that we are going to overwrite whatever value we have, which would be the same value. Again we would go to 2, we would again create another clone, again we would go to 3, again we would create another clone, again 4, again another clone. So basically we are going to end up inside the loop again and again infinitely. This is almost like Infinity War. Thanos is gonna snap his fingers, something like that, because we are completely destroying our computers resources, our company's resources, because it's an infinite loop. It's never gonna stop. So, and the reason it's never gonna stop is because we are doing the repetitive work again and again and again, and that is the issue. So somehow we need to resolve the issue. So how we are going to resolve the issue? Well, basically the idea is simple. If at any point, suppose we create an additional data structure, in that additional data structure we keep track of whatever the value we have traversed already or we have cloned already. If we know that, which means that initially when we start, we are going to check in that new data structure first that, hey, this element, have I cloned it already? If I have cloned it already, I would skip over, I would go to next element. If I haven't cloned it already, I would create a new clone of it, and then I will put the same entry in the hash map first before I go to the next element. So that way, when after this first circle comes and when I come back to the same position, I would know that, okay, I have already calculated this one, which means that I don't need to calculate it again and I can skip over it. First of all, let's see that what kind of additional data structure we are going to create, where we can immediately find that whether we have visited any particular element or not, which means that we are going to do a lot of searching. Hence we will need a data structure that is very quick and efficient in terms of finding the any element, that whether it contains that element or not. And the answer is pretty simple. If that kind of scenario happens, we need to use hash map or hash stat or something with the hashing. We cannot use the linked list over here. It would work fine, but it's going to add that much more additional time strain or on our system. So make sure that you justify your reasoning. I mean, in the interviews, people are not typically going to ask that why did you use hash map? This is a given. But the thing is that thinking should be clear in your mind that why you are using it. And in most of the graph problems, typically hash map is being used. Now inside this hash map, we are going to store two values. So as a key, we are going to store a node, and as a value, we are also going to store the node. But the thing is, as the key, we are going to store this input node, and as the value, we are going to store the cloned node that we will create. So let's see that what should be the algorithm for our solution and how we are going to approach it. So initially we start at this position 1. Now at this position 1, first of all, we check that whether we have this entry inside our hash map or not. Okay, we don't have the entry inside the hash map because we can find it in constant time. If the entry does not exist, we first of all create a clone node. Okay, clone node has been created. Now after creating the clone node, immediately before even we check for the neighbors of this one, immediately we are going to add an entry inside the clone node. So the value would be the cloned value that we have created, and the key would be the original input we are given. Now this is done. Now we are going to check for this one's neighbor. So let's say we end up at this neighbor number 2. So again, for this neighbor number 2, first of all, we are going to check that whether neighbor number 2 exists in this hash map or not. It does not exist, so we will create a clone. Now the clone has been created. First we will add the value to the hash map, and after adding the value, we would again go again recursively do find for the 2's neighbors. So in this case, the 2's neighbor would be 3. So we will create first we will check that whether 3 exists in the hash map. 3 does not exist, so we create the node and then we create this one. Now again we check for the value number 4. 4 does not exist, so again we create an entry inside the hash map. We provide the key value and then we create the clone node 4 again. Now for the 4th, we again check for its neighbor. So 4's neighbor, one neighbor is 1, which we already have it in hash map, which means that now we can ignore this case because we have already dealt with 1. Now second neighbor for 4 is 3, which already exists in the hash map, which means we can be dealt with it. We go back, 2 is already done, 1 is already done, which means that now we are running out of neighbors to track from inside the given original input. And we know that the original input is completely connected graph, which means that there is at no point there is a possibility that there exists some value 5 over here that is part of this graph, but it is not provided using this connection, because all the elements are connected, which means that this would be our final clone graph that we need to return. So after the loop ends and the recursive termination cases trigger, we can simply return whatever the clone graphs we have found, because from any single location we are able to guarantee to reach all the other elements. And once that is done, essentially we are done. So this is a very effective solution. Basically all we are doing is just we are traversing over the given graph, and during the traversal we are doing something. So in this case we are cloning it. We are using the hash map to keep track of whatever the visited elements that we have been through, and this solution is pretty efficient. It's not the most difficult problem in the world, but the thing is I am very bad at graph problems. So and I have always been scared of graph problems, but the thing is now I have decided to spend more time on graph problems, because if you want to join Facebook, you can't even think about not doing graph problems. Okay, so today is first of many problems to come. If we see the time and space complexity, the time complexity in this case would be big O of V plus E, where V is the vertices and E are the number of edges, because notice that over here we are only doing this much work, we are not doing any additional work. So that's pretty simple. And in terms of space complexity, it would actually be big O of V in terms of number of vertices, because over here we had 4 vertices, and in the hash map we created 4 entries. So whatever the number of vertices we are provided, we are going to use that, and that would be our space complexity. So this solution is actually pretty efficient. We are using depth first search to solve this problem, but even we can solve it with using breadth first search. So it makes no difference in terms of time complexity. The thing is, I just did this using depth first search. Next one I'm going to use breadth first search maybe. So first of all we are going to create a new hash map, and we are going to name it visited to keep track of whether we have already visited the node or not. Now inside the method, first of all we are going to check that if the given node is null, which means that we can return the node. Okay, and also we are going to check that if we have already visited the existing node, then we are simply going to return whatever the value we have stored inside the visited hash map. Okay, if this is not the case, first of all we are going to create a clone node. So let's just name it clone node. And inside the clone node we are going to give it the value of whatever the node value that we currently have, and we are going to assign a new array list. We are going to add the new clone node to the visited node. We are going to run a for loop for all the neighbors of existing node. So inside the loop, we are going to iterate over the neighbors of the existing node, and we are going to create the clone nodes for that. And inside the current clone node, we are going to put the neighbor as an array list. So, and over here we are going to make the recursive call with the neighbor. After this loop ends, we are simply going to return the clone node. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. There is still room to make a lot of improvisation, as we can see that our solution is not the most efficient. But the thing is, I'm really bad at graphs. So it took me a lot of time to make this video because I need to understand very thoroughly by myself first before I can create the video. But soon I'm going to do a lot of graph videos. So so my video quality is gonna improve and also my coding is gonna improve. So hope for the best, and let me know in the comments what do you think about the video. And yeah, see you next time. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do course schedule lead code problem, and this is one of the most versatile problem that has been asked at bunch of different companies, like huge number of companies. We can see the companies like Amazon, Microsoft, Facebook, Google, TikTok, Snapchat, Robinhood, Twilio, Uber, eBay, Tesla. All the companies have asked this question, and this question is very practical, real life application. So that's why a lot of companies like to ask this question. So this is a LeetCode medium problem, and we are given a number of courses, and we are also given an array of prerequisites where any single entity in array is defined like this, where we are given two values, suppose A and B, separated by a comma, which means that we must complete course B first in order for us to complete course A. So suppose we are given an entity in the prerequisites like this 1 and 0, which indicates that this course 1 actually has a prerequisite called course 0. So we can define it like this, that course 1 has a prerequisite on course 0, and in terms of the practical manners, we first complete this course 0 in order for us to complete this course 1. And based on the information given, we need to check that whether we can finish all the courses or not. And if we can finish all the courses, depending on whatever the prerequisites we are given, we need to return true, otherwise we need to return false. Okay, now that we understand the problem statement, let's take a custom example to understand the problem. Suppose we are given the list of prerequisites like this, and we are given the number of courses as 4, which means that we need to complete the 0, 1, 2 and 3. These 4 courses we need to complete, and this is the list of prerequisites we are given. Now we can consider this as actually graph problem. We can consider these as graph nodes, and the prerequisite information we can treat them as graph edges. So over here we can say, let's plot it on a graph and let's see that how it would look. So over here 1 has a dependence on 0, so I mentioned this. 0 has a dependence on 3, so let's also mention this. And 2 has a dependence on 0, so 2 has a dependence on 0. Okay, so this is how we can plot this on a graph, and we need to see that whether we can complete all of these forces or 4 courses or not. So the most intuitive solution is to check from the beginning. We check at this course number 0, that can this course number 0 be completed or not. Now in order for us to complete this course number 0, we see that this course 0 actually has a edge pointing towards course number 3, which means that course 3 is a prerequisite for course 0. So we need to complete this course 3 before we can complete course 0. Now we are at this course 3 again. We check the same thing, that whether we can complete the course 3 or not. Now course 3 does not have any prerequisite, which means it can be completed on its own. So we say that okay, course 3 can be completed. Now again we backtrack to 0. At 0 we check that does 0 have any other prerequisites that we need to take care of. No, 0 only has one prerequisite on course 3 which we can complete, which means that we are able to complete course 0 as well. So we can mark this and the square box indicate that we are able to complete that course. So we are good. So we already know that 0 can be completed, 3 can be completed. Now we check for this course number 1. So at course number 1, we check that what are the prerequisites for course number 1. Well, course number 1 has a prerequisite on course number 0. So since we already know that course 0 can be completed, which means we can also conclude that course 1 can also be completed, which we can mention over here. And we can check for this course number 2. So course number 2 also has a prerequisite on course 0, which is already done, which means we are able to complete course number 2 as well. So in this case, for all the 4 courses, we are actually able to complete them, and we can return true in this case, that yes, based on the given number of courses and prerequisites, we are able to complete all the courses. Now we need to check that what could be the scenario if we cannot complete the course. So suppose we are given an additional edge like this in the same example. Suppose we are given this additional edge. Now let's see that how the dynamic would change. Let me clean this up a bit. Okay, now we have this additional edge 3 2, which means that in order for us to complete this course number 3, we would need to complete course number 2 as well. Now let's see that can we complete. So initially we would check that can we complete this course 0. So in order for us to complete course 0, we would need to complete course 3. Okay, now in order for us to complete course 3, we would need to complete course 2. Okay, and again in order for us to complete this course 2, we would have to complete this course 0. So notice that we are constantly stuck inside a loop. It's the same scenario where you need experience to gain a job and you need a job to gain experience. It's somewhat similar kind of example, that we are stuck inside the loop, which means that no matter what happens, we are not able to complete any of these 3 courses without completing the other one, because there is an interdependence between each other. And essentially in this case, we would have to return false, that we cannot complete all the courses. But the thing is, why did we had to return this false? Well, the reason is quite simple. Basically, in terms of graph manner, if we speak, what was the difference from this graph compared to this previous graph? Only this edge. And when we added this edge, what essentially we did was we introduced a loop inside our graph amongst these 3 values 0, 2 and 3. So we can conclude one thing, that at any given moment, if we've identified that there exists a loop inside our graph, we would be able to immediately return false. If there does not exist a loop and we are able to, from every single element, we are able to complete all these prerequisites, in that scenario, we need to return true. So now we have these 2 information. Let's see that how can we use them and how can we solve this. So suppose we are given an example like this, and these are all the prerequisites that we are given, and we need to complete the total 6 number of courses in order for us to conclude that this graph can be scheduled or not. So essentially we are going to apply the same logic. We are going to first of all take these inputs, we are going to convert them in a graph like this. Inside the graph, for every single course, we are going to see that whether we can justify these prerequisites or not, and at any moment, if we identify that there exists a loop, we will immediately terminate and return false. If there does not exist a loop, we would keep going, and eventually we would return true. So that is the idea. And in order for us to achieve that, first of all, what we are going to need is, we are going to need some sort of graph data structure, because initially the only 2 values we are given is number of courses and the set of prerequisites. So first of all, we would create a data structure like hash map, and inside of our hash map, we are going to store 2 values. We are going to store as a key, we are going to store the number of courses, and as a value we are going to store the number of prerequisites that every single course has. So initially we would have, so this is the number of courses and these are the prerequisites that we have, and we would try to see that can we complete all the courses or not. So first of all, we are at this course 0. So in order for us to complete this course 0, we need to see that what are the prerequisites for course 0. So for course 0, the prerequisite says course 2. Now for this course 2, what is the prerequisite? The prerequisite is actually course 3. Okay, and now for this course 3, the prerequisite is actually course 4. So here, and for this particular course 4, the prerequisite is actually course 5. So here, now we are at this course 5, we check that can we complete this course 5, and yes, we are able to complete the course 5 because there exists an empty list. So which means we can conclude that course 5 can be completed over here because there is an empty list. So again we backtrack, we go back to course 4. At this course 4, we know that course 5 can be completed. Since course 5 can be completed, we can also have an empty list over here because it defines that at any moment, if we are at this course 4, that course 4 can always be completed because its prerequisites are already met. So we can have an empty list over here. Now again we go back. If we go back, we are at this course 3. So in order for us to complete this course 3, we would need to set up an empty list over here because course 4 can be completed. That is done. Now again we come back to this course 2. At this course 2, again we will create an empty list, and now we are at this course 0. So at this course 0, we only have dependence on course number 2, so we can also have an empty list over here, basically defining that course 0 can be completed. Okay, so that is one observation that has been done well. Now, and see that we were only trying to calculate that can we complete this course 4, but we already concluded that we can complete all these courses as well, and we have already established them inside our hash map. So at any moment we only need to identify the remaining courses and not all of these courses that we have solved already, which means we are efficiently improving our solution. Second, we come at course 1. Now this course 1 actually has 3 dependencies, course 2, course 4 and course 5. So let's take care of each of them one by one. First of all, we will check that from course 1 can we complete course 2. So we check for this course 2 and we check that these prerequisites are already met because there exists an empty list, which means that we can eliminate course 2 from over here from the list of prerequisites because we know it can be completed. Again, we check the same thing for this course 4. Over here this course 4 we again have the empty list, so we can also eliminate the course 4 over here as well. And again we can repeat the same process for this course 5, that course 5 can also be completed because there exists an empty list, which means even at this position course 1 we can create an empty list over here. And now if we look at all the courses, the only prerequisites we have are just empty lists. And once we achieve that, basically we can conclude that we have already reached our solution and we can return true in this case. So this solution works perfectly fine. But the thing is, we missed the key point over here. Like, because this was a true scenario, we did not identify any issues. But the thing is, if there was a loop, we were not actually checking that whether we are encountering any loop or not. So let's see that if we want to encounter any loop at any iteration, what would be the additional steps we need to take. So let's modify our example a bit. Suppose we have an additional prerequisite like this 5-3, that in order for us to complete this course 5 we will need to complete course 3. So we will have an edge like this, and let's modify our prerequisites table. Okay, now in this example we know that there exists a loop between this 3, 4 and 5, so we need to take care of it. And in order to take care of it, I'm suggesting that we create an additional hash set at the beginning of checking for any single course. So we create a hash set, and in our hash we just name it as visited or something. And over here we will keep track at any location are we repeating the same element. So let me show you what I mean by that. So initially, suppose that we are at this course 0 and then we start our program. So we want to check that whether we can complete course 0 or not. So first of all, we will check that whether we have already visited this course 0 in this current iteration. So we check in this visited node that have we visited course 0, and because it's a hash set, it's a constant time operation, so we are not adding any additional strain on the time complexity. So we haven't visited this node 0. We would add an entry over here first. Now we will check over here that what are the prerequisites for this course 0. So the prerequisite is course 2. So again we would check our visited node first. So course 2 is not part of it, so we would add an entry over here. And again we would continue over here. So now we need to check this course 3. Again we would add it entry to the visited node. We check over here, we need to check course 4 we haven't visited, so we would add an entry over here. Then we would check the force prerequisite 5 we haven't visited, so which means we would add an entry over here. And now at this 5 we would check the prerequisite for 5. So for the prerequisite for 5 is actually 3, so we are again at this position 3. So first of all we will check that whether we have visited this 3 or not, and this time we would know that yes, we have already visited this node 3, which means that we are in a loop. So this is what this hash set confirms, and the moment we find out, we can immediately return false over here. We don't even need to check any additional items in this given graph, and we would be able to terminate our case immediately, which means, and in case if this edge was not existent, this entry for this value number 5 we wouldn't have to check anything, and we would have been able to complete all of our code, and we would have been able to return true, but which is not the case this time, because there exists an additional prerequisite as specified over here. So this would be our final solution. And now let's calculate the time and space complexity for this one. So for time complexity, we can actually complete this whole thing in big O of v plus e time, because at any moment the maximum traversal we will have to do is from one node to all the single nodes, and throughout all the single edges. So this would be the time complexity. And space complexity, because we are creating an additional data structure like this hash map and also this hash set, but the thing is hash set is going to be smaller, so we are only concerned with this hash map. For general time complexity, it would be space complexity, it would be big O of v plus e as well. And okay, first of all we will create a hash map, and we are going to store integer and list inside it. We will name it course graph. Okay, now we will have to build our graph. So essentially we are going to iterate over every single prerequisite in the given prerequisites, and first of all we will check that whether this prerequisite is already added in our graph or not. So if it is added already, we only need to append the new prerequisite, and if it does not exist, we will need to create a new one. We'll have to create a new entry in our course graph. So we will create a new list and add the list, and then we will add the entry of the course and the list to our graph. Okay, so after this loop ends, we should have our graph structure ready. So now we will create a hash set that will take care of integer values, and we'll name it visited. And now we will have to run a loop for all the courses that we are given. And now we will have to create a method to check that whether there exists a cycle inside the loop or not. And let's name our method that course schedule, which indicates that whether we can schedule a course or not. In this course schedule method, we are going to provide the current course, the visited node, and the graph that we had created. And if this responds back to false at any given moment, we would know that we cannot create the course schedule, so we will return false immediately. And if this loop ends and we don't return false, which means that everything was successful, and we can return true. Okay, now we will have to create this course schedule method. So let's create a boolean method. Now let's test our terminating cases. So if our set contains the current course, which means that we have detected a cycle, so we can terminate immediately, so we can return false. Also we check that if for the current course, if we already have an entry in the graph where it has an empty array list, we can return true. If that is not the case, we will have to iterate over all the prerequisites for any particular course. So first of all, we will add the current course that we are iterating over in our visited hash set. Then we will iterate over every single prerequisite for that particular course. We would call our recursive function. So and we will provide the current prerequisite we are at. We will provide the visited hash set, and we will provide the graph. And if at any point this returns false, we can return false immediately. However, if this loop executes, we know that for that particular course we are actually able to complete the course and we can schedule it. So first of all, we will remove it from the visited node, and then now since we know that this particular course can be completed, we would update the entry for that course in our course graph. So we would set the prerequisite to null, which means that in future at any point if we identified this particular course, we know that we are able to complete it and we can just move forward quickly, and at the end we can simply return true in this case. So I guess this would be our course schedule function where the main logic happens, and let's try to run the code. Okay, seems like our code is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. So I would be putting this solution in the comments. You can check it out from there. And this was a really long video. It took me a lot of time to make it. So I hope you like it, and let me know in the comments on what are your thoughts about this problem. See you next time. So today we are going to do course schedule to LeetCode problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well liked problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses define. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses, and definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with 2 courses. So the 2 courses are going to be 0 and 1. Now for these 2 courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites, so let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky, and the tricky part is that we need to complete course 2 in order to complete course 0, which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course. Because definitely in order to complete course 1 we need to complete course 0, in order to complete course 0 we need to complete course 2, in order to complete course 2 we need to again complete course 1, but we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory, and for the graph we need 2 items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself, and for the edges we are going to take all the values that are present inside the prerequisite table, and based on that we are actually going to create an edge, and that is going to give us very interesting results. Now in this case, say for an example, just consider this example and let's try to draw a graph in this case. So first one, okay, we are given 4 courses, so we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite, so that's why there is an edge between 0 to 1. But the thing is, for 0 there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2 there is also going to be an edge, because course 1 is a prerequisite of course 2, and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have two ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse. And so let's try to stick with adjacency list. Now, based on this given array, we would be able to create our adjacency list. Now, how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map. Now inside this hash map, we will have to take care of two values. First one is like the key, and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for whom it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, our graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay. Now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the 3 tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use the DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. There is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we added. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all, we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. We are, for any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. What this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay, so first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6, we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0, currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack, and now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome, let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, there this has been jumbled up, so let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1. so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1. Okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received is this a valid answer or not. Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5, okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. Course number 1, course number 1 only had prerequisites on course 0 and course number 3. Both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use, and this is a great way to solve this problem. See, time and space complexity. In this case, the time complexity is actually going to be big O of v plus e, where v is the number of vertices and e is the number of edges. And if we see space complexity is also going to be big O of v plus e, and this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you, you also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay, so first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the stack or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a boolean value is possible that is going to check that whether we have been able to find any cycle or not.
And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color, and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method, that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that the color, where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it, and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. Recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what do you think about this.
Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. The thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island on somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean. And the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area. And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3. It will also go to cell 1 and cell 2. but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5, so water can't travel like this. Now the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel where if the rainwater falls it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here. From this 3 the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4, and from this this is at the edge, which means that at any point whatever the height over here is, like 1 2 whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4, so we can't go Pacific in this direction. If we try to go over here, we can reach to this 1, we cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean, so we wouldn't include this in our intersections. For every single cell we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater, so we wouldn't include this. We would go to next one. So over this again can reach to Pacific, but it cannot reach to Atlantic because it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5, so we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic, so we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells, so we can say that the time complexity would be big O of M multiplied by N squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given, and at any particular location we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that, okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean, and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true, because we know that they can reach to Pacific Ocean. Now, previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? And the moment we find that, okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6, so we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach, we were actually checking that whether the height we are currently at and the height the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case, this is 3, this is 6, which means that, okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here, because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix, or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell, we are not going to check the whole thing. We are only going to check the cell that is exactly adjacent to it. Suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean. We have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route, we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean. So this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. But it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this we need to iterate over the entire matrix, and in order to iterate over the entire 2D matrix, we have basically two methods. We can use either breadth first search or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here, and of course we can use recursion because notice that at every single position, so over here first of all we define that this can reach to Pacific Ocean. Now we move on all the directions, and over here we find the height difference. So again we know that this can reach to Pacific Ocean because this can reach to this cell, so we mark this as true, and then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over for any particular cell. We will have to iterate over all four of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these four entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array row and column wise, and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So after this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before. And if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know how do you like the video. Hello friends, the problem we are going to do today is one of the most versatile, most asked question in the history of LeetCode questions. Like if you just look at the sheer numbers of the amount this question has been asked and the range of companies this question has been asked, it's just mind-boggling. Whatever your dream company might be in the entire world, and if they do good technical interviews, they must have asked this question probably at least 2, 3, 5, 10 times to their candidates. If I only had 10 minutes to prepare for a technical interview, I'm going to choose this question at the top of my choice. Like just look at the companies over here, like Amazon, Microsoft, Bloomberg, Facebook, Google, LinkedIn, Oracle, Apple, ByteDance, which is basically TikTok, DoorDash, Yahoo, Paytm, Walmart, Tesla, Samsung. So I doubt that there are any companies left that didn't ask this question. And the question we are going to do today is number of islands, and I'm going to pay my utmost attention to this problem. Now in the input problem, we are given a grid of m cross n as a 2D binary matrix. And in this particular grid, we are all the cells are filled with either values of 1 or value of 0. And whatever the value that represents as value of 1 actually represents land in the real life, and all the values that are marked as 0 is actually water. And we need to find that what are the total number of islands inside this particular grid. Now based on the definition, we know that suppose if we have some sort of body of land, something like this, and if it is entirely covered by body of water, we can say that this particular body of land is actually an island. And we that is what we are trying to find in this given problem. Now we are also told one more thing, that at the edges of this particular grid, like all of these values, this is also water, which means that suppose we are given an input like this, where all of these values are zeros, and we only have just one single one over here. This we can also conclude as an island, because on these three sides of the island is already water, and on the outside is also water, because we are told that everything on the outside is also water. So just keep this in mind, that if we find some place at the edge of the grid, we still consider it to be surrounded by water if all the other side inside the grid is also water. And our aim is to find that how what is the maximum number of islands that are present inside the given grid. Now this problem is actually pretty simple. Like if we just see over here, like in this particular input, if we try to find for this example one, that how many number of islands there exist, actually there only exists just one island, and that is this one. Because notice this, that these all ones are actually able to be connect with each other, because they are adjacent to each other. If for any particular cell, suppose this is marked as 1 and this is a part of land, and any cell adjacent to this cell is also marked as 1, we can say that both of these are a common part of land, because there does not exist anything in between. They are right adjacent to each other, and this is what we are given over here. So in this example, we can only find one island. Now if we take the second example, we can see that there are actually more than one islands. So this is the first island that we can find. This one is by itself, and if we see all four sides of it, this is 0, this is 0, this is 0, and this is 0. So this is also an island, and these two ones, they are also an island. So in this example, we actually have three distinct islands. Okay, suppose we are given a custom example like this, and I have mentioned in my previous videos that it is really important to come up with your own custom examples, because it shows that you can think on your own and you can create test cases on your own. It's a really important skill for any computer engineer to have. Now suppose this is the grid that we are given, and this blue line indicates the body of water we have outside of our original grid. So this is just for understanding purposes. I'm just going to get rid of it now, so it does not become an issue, and I can explain the problem better. So we know that there is water outside. Now the most basic approach is that we start traversing through the entire grid in some manner. Like there are bunch of different ways to traverse through the given grid, and we try to see that at any moment if we find one, which means that so far we have find a body of land. Now since we have found this one, we need to see that what are the different islands we can create, and we can create bunch of different islands if all the values are relate are connected with one. Like no matter how many number of values are connected with any single one, we would mark all of them as just one island, as long as they are connected with each other. And basically what we are doing is we are trying to find separate set of ones. understand what I'm saying. We are I will repeat, we are trying to find separate set of ones. So in this example, if we just see that how many different sets we can find, like we can find this one set of 1, we can find this another set of ones, and we can find this third set of ones, and over here we only have one individual element, but still that is a set on its own. Like even if we only have just 1 acre of land, it's still a piece of land which we can consider as island. So that is what we are trying to find. And let me just revert back. Okay, so now we know that what we are trying to find. The most basic approach is we start traversing through the given input array, and we start traversing. Okay, suppose we traverse the first row, we don't find anything. Okay, now again we start traversing over here, we don't find anything. Now at this point we find that okay, there exists an element 1 over here. The moment we find that there exists an element 1 over here, we are going to call our function, and basically what that function is going to do is it is going to iterate over all the adjacent cells, and it is going to keep on iterating till we exhaust all the ones that are connected with this one. So till we exhaust all the sets that are associated with this particular one. So let me just go back a bit, and this is the approach we are going to take. That initially, currently we came to this particular item, we find that okay, there exists a 1 over here. Now because there exists a 1, we need to find all the ones that are connected with this one. So what we are going to do is we are going to mark this coordinate, and once we have this coordinate location, first of all we are going to increase the number of islands we have. Like initially the number of islands we have is 0. Now because we find at least a single one, which means that we have found at least one island, so we will update the number of islands we have. Now since we have already updated the number of islands, and we already have coordinates for this one, first of all we will mark this one as 0. So let's mark this one as 0. Okay, and now from this coordinate we will try to find all of its neighbors to see that there exist any adjacent ones. So over here we find that okay, this one is also 1 and this one is also 1. So we are going to repeat the same process, and remember, we are not going to update our islands in this case because we are still connected with whatever the previous value we had found before. So we are still in the same set of 1 that we were dealing with, so there is no point in updating that, but we have to exhaust all the ones that are connected with this original one we had found before. So we will check over here. Okay, this is 1. So because this is 1, we will will change its value to 0, because it now it becomes part of this original set we had. Now again we are from here we are going to repeat the same process. Okay, we don't find any ones from this point, so we are good. But remember, over here we didn't exhaust all the possibilities from our original coordinate, so we still have to do some work. So again we will come back, we will find 1 over here, which means we will have to turn it to 0. So we will convert this 1 to 0 as well. And now from this particular position we will try to repeat the same process. So we will check all of its neighbors, and all of its neighbors in this scenario are now 0, which means we are good. Like we have at least exhausted some possibility, and we have at least found one set of island. Okay, now we will again repeat with our process, and notice that I convert all these 3 values to zeros because we already found an island over here. And now we will repeat the same process. So again we will start traversing our matrix, and over here we encounter the 1 again, which means now we have encountered a new set of island. So we will update the value in our islands, we will update this to 2. Again we are going to repeat the same process. So first of all we will update this one to 0, and now this is 0. We still have to check its neighbors. We find an adjacent neighbor, again we flip it to 0 first, and again we go to the next element, again we flip it to 0, and now we won't find any more neighbors that are basically 1, which means that again we will start traversing. So we keep on traversing over and over and over, and we don't find any ones. But now we are at this point, again we find a 1, we update our island, so our number of island becomes 3. And now we need to find all the neighbors that are present in this particular island, and we set up all of those values to 0. So these values are set up to 0. And now we check that okay, no neighbor actually has a value of 1, which means we have exhausted all the possibilities of number of neighbors that could be a part of the island. And now again we repeat the same process, and now we find this one, and this is the last element. So again we increase the number of islands that we have found to 4, and we set this up to 0. And now because we have exhausted all the possibility and we reach to the end of the grid, we can simply return whatever the value we find in the number of islands, and that would be our solution. Suppose we were given an input with all the zeros, like over here we wouldn't have found any island, and we can simply return 0 in that case as well. But this is like a very basic approach, and the approach we took in this scenario is actually depth first search, to find the set of ones that are adjacent to each other. Like we could have used BFS as well, but I mentioned earlier, like I'm trying to learn graph theory, and first I'm going to master DFS, then I will start working on the BFS. So that's why I decided to choose the approach of depth first search in this scenario. Okay, and the time complexity in this case would be actually big O of m cross n time complexity, because that is in we have to iterate over entire grid that is given. And the space complexity would also be big O of m cross n in the worst case scenario. Suppose that we are given a grid where all the values are just ones, which means that for any single element we will have to iterate over all the entire grid, and that could be the worst time in space complexity. First, we'll create two parameters, row and column, to calculate the current row and column values for the given grid. Okay, and we'll also create a variable called island, and initially we will set it up to value 0, and we would update this every time we encounter 1 inside the given matrix. And inside the loop we will have a condition that if the current I and jth position inside the grid is actually equal to 1, then only we are going to call our DFS function. So first we'll do island, we'll increase the value of islands, and now we'll call our DFS function. In the DFS we are going to provide the ith position, the jth position, and we'll also provide the grid that we are working on. And once this loop ends, like we should have all the set of separate ones, and we should have all the values of the total number of islands. So we can simply return the number of islands we have found. Okay, now we need to create the logic to implement this DFS function. So first we'll create a function. Inside the function we will need the values for the row and column again for the entire grid. So we'll just name them new row, and this would be grid's length, and we will also create a parameter called new column. This would be the first position's length. And this is basically the same as finding the row and column we found over here, but we need to use it, so I'm just giving different names. We'll also create a 2D array of called directions. This would make our lives easier and allow us to iterate over all the adjacent values of any current position, and we are going to initialize it with default values. We have this established. First we will put a condition that if the current row and column are they out of bounds or not. We will also put an additional condition that if the current value we are at inside the grid, if that is already 0 or not, because if that is already 0 we won't have to do anything. So if any of these conditions satisfy, we can simply break out of the DFS function, and this would be our terminating case. If this is not true, first of all we will update the current position we are at inside the grid, and will enter the value as 0, because remember we have already updated the islands. And now we will just run a for loop and iterate over all the 4 directions. So that will allow us to go over all the neighboring candidates of this row and column that we have. And now we are simply going to call DFS on row plus direction of 0 and column plus direction of 1, and we will also provide the value of grid as well. And yeah, I guess this should be our logic, and we can try to run this code. Okay, looks like we messed something up. Oh, okay, seems like our solution is working. Let's try to submit the code. Seems like our solution is also working, but hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do longest consecutive sequence problem, and this problem has been asked in Google, Microsoft, Facebook, Apple, Goldman Sachs, Uber, Twitter, ByteDance. So it's a lot of companies and a lot of huge ID companies that have asked this problem. So I'm going to pay my most attention. I hope you also do it. And I just have one request for all of you guys. Like my YouTube channel, if you see, most of the people, they are not even subscribed, and it takes a lot of time and a lot of effort to make these videos. So I would really appreciate if you can just subscribe. Like basically we are given an unsorted array of integer nums, and we need to return the length of longest consecutive elements inside the sequence. Also there could be possible that there might be duplicates in our given unsorted array, so we just need to take care of those as well. And let's try to understand this with an example. So the example we are given over here is, and over here if we find that what is the longest consecutive sequence we can find, the longest consecutive sequence we can make is 1 2 3 4 amongst these values, and we can ignore just this 100 and 200 because there does not exist any consecutive sequence from those values. So over here since we found 4 elements, we can return the length of this as 4, and this would be our answer. Same way if we take another example, over here we are given 9 elements, and all 9 elements are actually part of the longest consecutive sequence. So in this scenario we are going to return 9. So in the brute force approach, we are not going to do anything clever. We are just going to take the most basic approach that we can and try to find the longest consecutive subsequence. So suppose at any moment we are given an input like this, we are given an empty list. We can say that there exist 0 longest common subsequence elements, and suppose we are given an element like this, suppose this is 100, we can say that there exists exactly 1 longest common subsequence element in this given input. So that is a given, right? That even if with a single element, we can at least define that there exists 1 single longest common subsequence element. Now over here in this example, since we know that there are at least more than 0 elements in this given input, and initially we are at this 100th position, which means that we can say that the current longest consecutive subsequence we can find is 1. And now if we want to find a subsequence in the remaining group that consists this 100, how can we do it? Like we can only do it in one scenario, that in this remaining portion, in this remaining elements, if there exists element 101, if this exists, we can say that 100 is also part of the or could be part of the longest consecutive subsequence. So this would be our basic approach. that at every single position we will try to find that whether the next elements could they be in the remaining input, and if they do, we will update our longest consecutive subsequence, and whatever the maximum value we find, we are going to return it as our answer. So we will also create another variable called current subsequence, and that would take care of what is the current subsequence that we are trying to find. Let's just name this current. Okay, and initially the current subsequence is also at also 1 over here at this 100th position. Now we'll try to see that whether this 101 exists in the remaining portion, and it does not exist, which means we will move forward. So we'll move forward with the element 4. Now for this element 4, we need to see that whether element 5 exists or not. So element 5 also does not exist, so we'll move on with just 200. For 200, we will see whether 201 exists. This also does not exist. For this one, we will try to see that whether 2 exists. So 2 exists in the remaining array. Now because 2 exists, the current subsequence we had was of value 1. We will update it to value 2. Now because this 2 exists, we can not break right now. We'll try to find more values. So we'll again try to see that whether 3 exists, and 3 also exists, which is over here. So again we will update this value to 3. Again, because 3 exists, we will try to see whether 4 exists. 4 also exists, and it is present over here. So we will update the current value of longest consecutive subsequence we have found to 4. Now we will try to see whether 5 exists. Now 5 does not exist, which means that 4 is the longest we have found so far, and then we will try to update the value of longest consecutive subsequence we have found to whatever the current value is, because previous value of this was 1 and now this new value is 4. But we are not done yet. We have only checked up until this 1. So now we will check for this 2. So again for this 2 we will, and by the way, we will re-evaluate this value back to 1 because now we are starting with the new element. So again for this 2, 3 exists, so we will update the value to 2, and 4 also exists, so we will update the value to 3. But we cannot update the longest common subsequence because 4 is greater than 3. And now we again check for this value number 3. So for value number 3, 4 also exists, which means that this value would become 2 for this value number 3, but we won't update, and in the end we are going to return this 4. So this is our brute force approach. Like, this solution works, we get the desired answer. But the thing is, we get the desired answer at a very bad cost. Like, even if we just try to calculate the time complexity, in this case the time complexity would actually be go of n cube. Why n cube? Because we will need to iterate over every single elements at least once to find the longest common subsequence. So that is n amount of work. Then suppose over here we are initially at this position 100. So we wanted to check that whether 101 exists. So in order to do this check, we will also have to iterate over the entire loop. So then in that case, we will have to do n more work. And at any given moment, suppose over here we identify that for this one, 2 also exists, right? And once we identify that 2 exists, we will again check whether 3 exists. Again we will check whether 4 exists. Again we will check whether 5 exists. So even to do these checks, we will have to do n more work. So again we will do n work. So in total we are going to do n times n times n. So n cube work to solve this brute force approach, and this is a very disastrous solution. Now one better approach we can think of is, suppose that with the given input, if we do some sort of modification, can we come up with better solution in faster time complexity? Like, of course we can. So remember that what we are needed over here is that we need to find the longest consecutive subsequence of this given input. And we are going to see with this custom example how can we modify the input and how can we come closer to solution. So suppose in this given example, rather than keeping the input just like this, if we do sort the given input, things become much easier for us. And let's see that what would be the sorted result. Okay, so now we have our sorted result. Now in the sorted result, we simply need to find that what is the longest common subsequence that exists, longest consecutive subsequence that exists. And it's pretty simple to find now, because all we need to do is that at any point we know that the definition of common subsequence is that suppose we are currently at the value I, then I plus 1 would be a common subsequence, then I plus 2 would be a common subsequence, and this is the only condition we have to take care of. And the only other thing we need to worry about is having two duplicate values right next to each other. If at any point we encounter two duplicate values, we simply ignore one of those values and move forward. So in this example, we are only going to do two checks with the sorted input. First check we are going to do is, at first position we are going to check that whether this position is exactly same as whatever the previous position we had. If that is true, we would skip over because we don't need to do anything with that, because there are two same values. And if that is the case, so which is the case in this scenario, that both values are same, which means we would skip over. So we would go to the next element, and now we are at this next element. Again we are going to check that the value we are currently at and the value before that, if they are same or not. So in this case they are not same. If they are not the same, we are also going to check one more thing, that whether the current value of a of I, so suppose this 0 is actually a of I, and minus whatever the value of a of I minus 1. So a of I minus 1 in this case is minus 1. So if difference between these two values, if it becomes exactly 1, which means we can conclude that these two values are part of the longest common subsequence, and we could update their value. Again like brute force, we are going to use two variables. One variable to keep track of longest common subsequence we have found so far, and second one is to keep track of the current subsequence that we are working on. So let's see that how it would work. And both the values would be set up as 1 initially. Now initially we are at this 0 and 1 pair, and because they are sorted, we know that they are always going to be adjacent to each other. So this is the only condition we need to worry once we identify that the both values are not same. So in this case we can say that the current subsequence we have found is actually size 2. So we can update the value over here, that this is 2. Now again we check with this value. Now this value, again it's 0, and it's the same as this one, so we ignore it. We don't need to do anything. Now again we check with this value. So this value is actually 2. Now with this 2, if we put down this equation, so 2 minus 0, this is not equal to 1, which means that this 2 and 0 are not part of the common subsequence. If they are not part of the common subsequence, we check that now we can't update this current anymore. So we check between the current and longest common subsequence we have so far, and the current is actually greater, which means we will update the longest consecutive subsequence to 2 as well. And now current, we will put it back to 1, because we will repeat our search again. Now we are at this position 3. So 3 and 2 are not same, and 3 minus 2 is actually 1, which is true, which means we update our current. So current would become 2. Now we are at this 4. Again 4 minus 3 is equal to 1. So again we update our current to 3. Again we are at this 5. So again we need to update our current. So current would be updated to 4, because all of these values 2, 3, 4, 5, they are in a common subsequence. Now we are at the 7. So 7 minus 5, they are not equal to 1, which means we can't update the current. So we will need to reset the value of the current. So before resetting the value of the current, we are also going to check that whether the longest common subsequence needs to update, and this needs to be updated to value 4, because this one was 4 before, because of these 4 values. And now we can set this value to 1 again at this position 7. And now we are at this position 200. So 207, they don't have any correlation, so we can't do anything about it. And in the end, at the end of the loop, we are simply going to return whatever the longest common subsequence or current subsequence, whatever the maximum value we have found between these two. And in this case, the maximum value we have found is actually 4. So this would be our solution. Now this solution works pretty efficiently. It's pretty neat. And if we see the time complexity, we can complete everything in just one single iteration. So we are only doing n work. But the thing is, the time complexity in this case would be go of n log n, because initially remember that from this given input we will actually have to sort the array as well, and sorting takes n log n time. But overall, if we still compare it with whatever the brute force approach we had, brute force was actually big O of n cube. So this was really bad time complexity, and this is much more and much bigger improvement upon our scenario. Now in the optimal solution, we are actually going to try a couple of things. First thing we are going to do is we are going to create an additional data structure called hash set, and in the hash set we are going to enter all the values that we have found from this array. So suppose we create a hash set something like num set. Now in this hash set we are going to add all of these values. Now because we have our hash set ready, what we are going to do is when we are going to iterate over this hash set, and we are only going to start checking for the longest consecutive subsequence from the elements that could be at the start of the start of the longest common subsequence. And what elements can be start of the longest common subsequence? Well, so if we take this example, we can actually see couple of common subsequences or consecutive subsequence. One consecutive subsequence we can find is 99 and 100, which is at these two positions. And second consecutive subsequence we can find is actually 1, 2, 3 and 4. Now in the what we were doing in the brute force is we were checking at every single position that what would be the longest common subsequence we can find. The thing is we can only find the longest common subsequence from the first element of the start of this consecutive subsequence. Same goes over here, that whatever the subsequence we can find at this value number 100, the subsequence that we can find at value number 99 would always be greater than whatever we can find over here, because this by itself is already a subsequence. So we are going to use this logic. Like over here, if we put this 3 to 3 4, we will only find the consecutive subsequence of length 2, but this 2 3 4 would be of length 3, and this 1 2 3 4 would actually be of length 4. So we can only find the maximum consecutive subsequence at the start of the any subsequence, not somewhere in the middle. And the only way to check that whether we are at the start of the subsequence or not is by just checking one very simple condition, that at any point we check that whether the exact value before that value, like one value before the value we currently are at, if that exists, which means that we are not at the start of the common subsequence. Let's take it by an example over here, and let's see that what would be our approach. So first of all, we are going to be at this position 100. We are going to check that whether this 100 is a start of any consecutive subsequence or not. So we check that whether in this given num set does the value 99 exist. Now we know that 99 exists. So because 99 exists, 100 cannot be at the start of the common consecutive subsequence. So we are going to ignore this case. We don't have to do anything with this 100. We come up at 99. Now we come up at this 99. We check that whether there exists a value before 99. So 98, does it exist in this num set? 98 does not exist, which means that at 99 we can be at the start of any common consecutive subsequence. So we start a subsequence at 99, and now we will initiate our logic. And in our logic we are simply going to check that from this 99 how many consecutive numbers we can reach. So we are going to check that, okay, 99 by itself is a common subsequence of length 1, so we know that. Now from this 99 we are going to check that can we reach value number 100. So 100 we can reach, and because we are using a hash set, we can do all the operations in constant time, so we are not adding any strain in our time complexity. Now we can find the value 100, so we can reach 100, which means that whatever the longest common subsequence longest consecutive subsequence we found, we will increase its value to 2. Now again we will try to see that whether we can find 101. Like 101 does not exist, which means we would break out of over here, and the longest common subsequence we have found up until this point is actually of length 2. Again we are going to repeat the same process. So now we are at this position 4. We check that whether 3 exists in this set or not. So 3 exists, which means we ignore this 4. Now again we are at 200, so we check that whether 199 exists. So 199 does not exist, which means 200 can be start of the any consecutive subsequence. So we again check that whether 201 exists, but 201 does not exist in this given example, so we ignore this 200 as well, because the longest consecutive subsequence we find at this value number 200 is always going to be 1, and we already have a value that is greater than 1. Again we check at this position 1, that can 1 be start of any consecutive subsequence. So we check that whether the 1 minus 1, so we check whether 0 exists in this example or not. 0 does not exist, which means 1 can be start. So now we set our current subsequence to value number 1, and now we check that from this value 1 how many other values we can reach to. So first we check that can we reach the value number 2. Yes, we can reach value number 2 because 2 already exists. So we update whatever the current subsequence we can find to 2. Now from this 2 we check can we reach 3. Again we can reach 3, so we will update the current value to 3. Again we check that whether from this 3 can we reach 4, and yes, we can reach 4 as well. So again we will update the value of our 4 value of the current subsequence to 4, and from 4 we check whether we can reach 5. So 5 we can't reach, which means we are at least able to reach this 4. So we are able to see that the current the longest current subsequence we have found is 4, and previous value was 2. So we will update this, so this will become 4. And now again we are going to check the same thing for this value number 2, so that for value number 2 does 1 exist, and 1 exists, so we will ignore this. Again we check for 3, does 2 exist, 2 also exists, which means we are going to ignore this 3. And now since we have reached the end of this hash set, so we are going to reach whatever we found in the as the longest consecutive subsequence, and this would be our answer. Now if we calculate the time complexity, the time complexity would actually be big O of n in this case, because we are only iterating over the entire input just once through this hash set. So this is a very efficient time complexity. And if we see the space complexity, the space complexity is actually big O of n, because we will have to create this additional numerical set, and we are going to store n memory for that. And let's see the coding. I will be showing the hash set solution in this code, but I'm going to post both the codes in the comments so you can check it out from there. So first of all, we are going to check that whether we are given an empty list or not. If that's not the case, first of all, we are going to create a hash set. We are going to name it num set. Now we'll run a loop across the given input, and we are going to store all the values to our hash set. This is going to do two things. It's going to eliminate all the duplicates values, and it will only add unique entries in the hash set, because hash set has a property that does not allow us it to store duplicate values. Now we are going to create a parameter to store the longest subsequence, and we are going to initialize it with value 1. Now we are going to run a for loop across the given num set. So initially we are going to check that whether we are starting from the middle of any longest consecutive subsequence. If that's the case, we are going to ignore that number. So if this condition is true, we are going to continue and go to next element in the loop. If this is not the case, we are first of all going to mark the number we are at as current number, because this is the beginning of any longest consecutive subsequence. We are also going to create another parameter called current sub, that is going to take care of the current maximum consecutive subsequence we can find, and we are going to initialize it to 1. And now we are going to put a condition that while our hash set contains the current number plus 1, while this condition is true, we are going to increase the number, and we are also going to increase our current subsequence. And after this loop ends, we need to check that whether we have found the longest common subsequence or not. So once this loop ends, we should have our answer, and the longest sub variable, so we can simply return that. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. And seems like our solution works pretty well, and it is faster than a lot of other solutions. I will also post the sorting algorithm solution as well, so you can check it out from the comments. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do alien dictionary lead code problem, and not only it is a very important problem, this problem can actually be asked in multiple ways. It can be asked directly as a graph question, or it can be asked as a follow-up question for the previous question that we solved, verifying an alien dictionary. Because both questions are very similar, and if you want to check that where the solution for this problem is, you can check it out from over here. Also, another reason why this problem is really important is if you just take a list of companies that have asked this problem: Airbnb, Facebook, Google, Amazon, Bloomberg, Microsoft, Uber, they have all asked this question in last 6 months. Also, IT giants like Pinterest, Apple, Twitter, eBay, they all have asked this question in last 6 months to 1 year. And ByteDance, Snapchat, and Flipkart, so they have asked this question not fairly recently, but still it's important. And I will be paying my utmost attention because my aim is to clear any FAANG interview, and I hope you also enjoy the video. This is a LeetCode hard problem, and it justifies this hard tag. So let's understand the problem statement. Essentially, we have identified a new alien language that uses English alphabet. However, the order of those letters is unknown to us. Now we are given a list of strings inside this words, and we are told that they are from this alien languages dictionary. And in that string, the important property these words have is that they are sorted lexicographically. And we need to return a string of unique letters that are present in these words, and we need to return them in lexicographically increasing order. Now also there could be possible that there might be multiple solutions, so if there are multiple solutions, we only need to return any one of them. And there could be some cases where this given string of words is invalid, and if it is invalid, we need to return an empty string. So in order to understand this problem, first of all, we will have to identify that what does this lexicographically increasing order means. The second thing we will have to understand is that what are the cases where this particular input is going to be resulting in falsified information, and what does this string of unique letters with lexicographically increasing order means, because this unique word is actually really important, and I'll come to that later. So suppose if we just talk about what is lexicographically sorted means, if we talk about English language, if we talk about the words A, B, C, D, all the way up to Z, this is plain English language that we use on a day-to-day basis. Now in the English, suppose we are given any 4 letters. Suppose we are given letters like Q, A, E, B, R, C, and Q, E. Suppose we are given letters like this, right? And if we want to sort these 4 in plain English language, how we are going to sort them? Like, of course, the answer is simple. We are only going to check that what is their position in this given order, and based on that particular order, we will sort them. So if we sort them, the sorted result would look something like EA, QA, QE, and RC, something like this, right? And the reason we are able to generate this is because we know that the position of E comes before Q, and in this case there are 2 entries, QA and QE. So which means, like, if we will have to identify that what is the second letter, and second letter A comes before E, and then this R actually comes before Q. So we are able to determine a sequence like this. Now in this given problem, we don't need to generate a sequence like this. Basically we are told that we are not given this information. We don't know that what is the order of words are, and we are directly given this particular sequence that is already sorted in that particular language. So suppose this was to be an alien language, and if we want to identify that what should be the answer we need to return in this case, the few things we can determine from this input is that, okay, over here we are checking first, at any point we are checking any two adjacent words. In those two adjacent words we go letter by letter and we try to see that what is the first differing letter that comes to the existence, and based on the differing letter, whatever the word is presented first should come first in that order rather than second second letter. So if we compare these two words EA and QA, we can see that the first differing word comes as E and over here it is Q. So which means we can determine that E will always come before Q in this particular alien language. Now don't forget this, that this is plain English. For just imagine this as an existing scenario. So we know one scenario, okay, that E should come before Q, right? Now over here again, if we compare next two words, the next two words are QA and QE. Okay, so in QA and QE, notice that the first letter is Q, so it is common, which means we cannot identify much information from that. But the second letter is A and E, which means we can determine that at any given scenario A will always come before E. So we can notify that, we can also create a scenario like that, that A will always come before E. And over here I am denoting this relation by an arrow, which indicates that at any given moment E should always come before Q, because it is on the beginning end of the arrow, and the where it is pointing to should comes later. And again we will compare these two words QE and RC. So if we compare these two words, we can identify that, okay, Q should come before R. So we can also denote that relationship, that Q will become will be before R, right? And over here now we have these three relations. So based on these three relations, we can actually establish something over here, that we can establish that A will always come before E, and E will always come before Q, and Q will always come before R. So one of the sequence that we can return over here is that A, E, Q, R. Okay, so this is one of the sequence that we have to maintain at any given cost, because we are given these conditions based on the words that were given. But the thing is, will this be our answer? And actually this will not be our answer. And the reason this will not be our answer is because over here we are given this particular line that we need to return a string of unique letters from this words in the new alien language, that is lexicographically increasing order. The thing is, over here if we look the original input, in the original input we actually have one more unique character that we are missing, and that particular unique character is, so we already took care of E, we took care of A, we took care of Q, A, Q, E, R, all of this we took care of, but C, the letter C, we did not take care of it. And the thing is, over here, based on whatever the input that we were given originally, we cannot determine the position of C. But the thing is, we know that C is also a unique character. And the only thing we know about the positioning is that for these four characters, we can define some positioning like this. For C, we cannot determine any positioning, but the thing is, it has to be part of the answer as well. And that is why we are told that there could be multiple solutions and we need to return any of them. So in this scenario, this could also be a solution where A, E, Q, R and C we are placed at the end. Or this could also be a solution where A, we put C somewhere in the middle, and E, Q, R is also placed like that. The important thing is that we need to maintain this order. As long as we are maintaining this order, because this C is one of those unique letters where we cannot find the dependency for that. So we will need to take care of it as well. And this is a very important detail that a lot of other videos have missed out. And that is why it took me a lot of time to make this video. I want to make sure that I go through it completely. Now let's take one more example from the given input. and we will again try to find that what should be the answer for that. So in the given input, we are given the following words. These are the words that we are given in the alien dictionary, right? And our aim is to find that what should be the answer in this case. Well, the first thing is that what we are going to need in order to generate the solution. In order to generate the solution, we are going to need two things. We are going to need list of all the unique characters that exist, and second thing we are going to need is what are the dependency on all between characters, and based on these two things we will try to generate some sort of order or some sort of pair. And also remember that we will have to consider the scenarios where we could find invalid strings as well. So I'll be explaining that in this example. So over here, if we see the list of unique characters, the unique characters are W, R, T, F, E. Okay, these are all the unique characters that we can find in this particular input. Okay, now let's start making dependencies. Now, in order to make dependencies at any given moment, we will have to compare two adjacent words, and we are going to find first differing character, and based on the differing character we are going to establish some dependency. So first of all, the first two words we are going to compare are WRT and WRF. Okay, in this case W is common, R is common, which means that first differing character is T and F, and we already know that these words are sorted. So because they are sorted, we can determine that T should come before F. Okay, we already know that. This is good. Now what are the next two words? Next two words, and we are done with this WRT. The next two words are WRF and ER. Okay, so WRF and ER. Now in this case, what is the first differing word? Well, the first differing word is first letter by itself, W and D, which means we can make another dependency that W should always come before E. Now we can ignore this. Again, we compare next two words. So ER and ETT. So over here, what is the first so EE is common. The first differing letter is R and T, which means that R should come before T. Next one is ETT and RFTT. So over here the first differing character is E and R, so we can also mention that E should always come before R. Okay, now we have these four dependencies for these 5 unique characters. Now let's try to create a dependency tree from this given input. So if we see, we can clearly see that okay, W is dependent on E, and E, so W comes before E, then E comes before R. Okay, then for R comes before T, and T comes before F. So this becomes all the dependencies, and if we notice all the unique characters, they are already part of these dependencies, so we are good. We don't need to do anything more over here. Now if we make that what should be the order of letters, the order of letters in this case would be W, E, R, T, F, and this would be the correct solution. Now notice that in order to generate the correct solution, what we had to do is we had to find all the unique characters, all the dependencies. Once we had all the dependencies, we actually had to iterate over all the dependencies, see that which dependencies are interconnected. Based on their interconnection, we actually had to generate this order. And in order to do that, we are actually using graph theory. And how we are using graph theory is basically all the unique characters in this case are actually nodes, and all of these dependencies are actually edges between those nodes, and those edges can be represented as in some form of adjacency list in some sort of hash map, and then we will need to iterate over all of the entire graph, and then at any moment we will have to go through the graph and find the solution, that what should be the order in which we are able to iterate over all the unique characters, which means that all the nodes inside the graph, and we need to generate this order of pairs And if we are able to successfully generate this order of pair, we will return whatever we find. And if for somehow we find out that the input is invalid, we will have to take care of that scenario as well. So first let's take a couple of examples where we can find that the input could be invalid. Now, based on the English language, we know that at any given moment, if there are two words present, W1 and W2, and we know that any single word, so suppose W1 is actually prefix of this W2, if that is the case, then W1 should always come before in the dictionary than W2. Let's take it by an example. Suppose we are given two words like bat and Batman. If we are given two words like this, so if we start comparing these two words and see that what should be their order, we check that okay, B is common, A is common, T is common, right? Now over here, this actually ends. There is actually an empty list. There is nothing over here. While over here, there are still some values. So if that is the case, we can determine that this W1 is actually prefix of this W2 because these three characters are also present over here. And in that scenario, this W1 should always come before W2. At any given moment, we identify that this particular character is not present in correct manner, and suppose we are given an input like this, that Batman and bat. If we at any moment encounter this scenario, we can immediately return false, because, or we can immediately return an empty string, because this is a wrong ordering. So this is one of the failed scenarios where we cannot do anything, right? So this is very important to understand, and we will have to take care of this in our solution. The second thing that will not work is that at any given moment, suppose we are given list of words, suppose the words are like X, A, B, X. Suppose we are given list of words like this, and what this means is that the first letter X should always come before A. Okay, so based on these two, we can establish this dependency. Based on these two, we can also establish that A should always come before B. Okay, and over here, the next thing is that B and X, which means that what this is saying, that B should always come before X. So if you notice over here, that we are actually stuck inside a cycle, that X needs to come before A needs to come before B, and B needs to come before X. So at any moment in our graph, whenever we are traversing over all these unique characters and dependencies, at any moment we encounter that okay, there exists a loop, and if we detect that there is a loop from any particular node, then we can return false immediately, or we can say that okay, this is an invalid case where the string actually doesn't exist, and we will need to break out of the loop. Suppose we are given a custom example like this, words, and we are told that all of these words, they are lexicographically sorted in the alien dictionary, and now we need to return the order of words of all the unique characters that we can find. So what should be the approach? Well, in order to do that, we are going to need two things. First thing we are going to need is all the list of all the unique words or all the unique characters, and we are also going to need the entire dependency between any two letters, that which should come first and which should come later, right? So let's start working on it. So first of all, we have B and A. Okay, so we will just add list of unique letters B and A, and second word is BY, which means that first differing characters A and Y. So we can establish a dependency like this, that A should come always before Y. Okay, now again moving forward with next two values. So over here, the first differing character is B and A, which means that B should always come before A. And also I forgot to add one more unique character Y over here, right? Now this B should come before this A, so we will add that to our dependency list as well, that B should come before A, right? So this is one dependency, and over here we have the unique character D, so we will add the unique character D as well. Now we have this another word, these two words, and in these two words A is common, which means that D and L are differing characters. So first of all, we will add the word L over here, and over here we have this D, right? So we know that D at any given location will come before L. Okay, so we'll just mention that. Now over here we have one more unique character T, so I'll also mention that. Now the next two words are these two words. Over here the A is common, L and I are different, and also we have one more unique character I. Now we know that there is a dependency between L to I, so we will also mention that L should come before I. Now the next two words are AI and AIR. Now notice over here that this AI is actually prefix of this AIR, right? Which means that this AI will always come before this word AIR, but we cannot determine anything regarding this R, because this R by itself, it has no other thing to compare its result with, which means that though we have a unique word, we don't know that what is the intention for that particular word is. And now let's see that in the dependency list that we have created, amongst these unique words, what are all the words that we are able to find a pair for. So one pair we were able to find is for this one, this BAY. Let me just draw everything in same color. So BAY, this is one pair, which means we know that at any given moment this BAY order has to be maintained, like B always has to come before A and Y. And same goes for this DLI, that D always has to come before L, and L always has to come before I. But in the list of unique characters, we are given this R and T as well, that are not represented by any dependency, which means we can say that this R and this T, they are unique characters by themselves, which does not have any sort of dependency, right? So if we want to see that what could be the potential different pairs we can make over here, well, there could be bunch of different results. Like there can be so many different permutations and combinations. Let me just give you a few of them. Like most simple one would be BAY DLI RT. So this is one combination where notice that we are just maintaining the entire order. Now second combination could be B D A L Y I R T. Now notice over here that at any given moment we need to make sure that these two orders are met up. So B is always coming before A and A is always coming before Y. So that is satisfied. Over here D is always coming before L and L is also coming before I. So that is also satisfied. This RT, they don't have any dependency, so it doesn't matter. We could have some pair like this, that B R T D A Y L I. This is also a valid pair, because notice that this B A and Y, this is maintained. This D L and I, this is also maintained. This position of R and T doesn't matter. So there can be a bunch of different options that we can choose from, and I'm just showing you that these are the different results we can have, right? Because we need to take care of unique characters as well. So don't forget the unique characters, they are really important. Now what should be the approach in this case? Well, one approach is actually quite simple. Because we know that we have unique characters, we have the dependency, we can choose some data structure like hash map. We can iterate over at any point. Whenever we identify the dependency, we can iterate over the entire hash map. We can, from any point, we will try to see that whether it has any dependency or not. If it has dependency, we will go to that dependency, we will try to iterate over those values, and we will try to generate the order list, right? So let's see that how it can work. Suppose we create a hash set like suppose we create a hash map like this. Okay, suppose this is our hash map, and based on these dependencies we know something, that we know that okay, for in order for us to put down this B, we know that A has to come after B, which means A has dependency on B, right? We will mention it over here. Now for this A has to come before Y, so A has to come before Y. Now for this Y, we don't have any dependency, so we will just leave this value as blank. Now for this particular D has to come before L, right? So we will just mention L over here. Now this L has to come before I, so we will just mention I over here. For this I, we don't have any dependency, so we are good. And same goes for this T and R, that we don't have any dependency, so we are good. Now since we have this dependency tree, let's see that what would be the approach we can take over here. So in this scenario, suppose if we want to calculate that what would be one of those ordering pair, what we can do is we will start traversing through all of these values, all of these unique characters. And remember that this is hash map. So in hash map we are treating these as key values, and these are actually values. So in the keys we are mentioning all the unique characters, in the value we are mentioning all the dependencies. Now over here we will start iterating at this b. So first I'll just mark b as that we are iterating over it, right? Now from this b we identify that okay, we need to have a before b. So again we go to a, because we will have to check all the dependencies, right? We cannot just put any letter randomly any place, right? Because this b has some dependency, so we will have to go over that. Now this a has actually dependency on y, so again we'll go to y and we'll just mark a as being as part of being visiting. And over here we reach at this y don't have any dependency, so we are at this y. Now notice that we are actually traversing this graph in DFS manner, depth first search manner, right? And in depth first search at this y we identify that okay, this y does not have any dependency, so we can just put y to our order list. So we can just put y to our order list. Now from this y we will do a backtrack, we will again come back to a, again we will do a backtrack, again we will come back to b, and then we would be done with this b, right? That okay, we are done with this. Now again we ignore all of these. Now we start with this second position. Now in the second position, first we determine that whether we have calculated this value already or not. So since a is already calculated over here, so we ignore that, so we can ignore the second case. Again we check that whether this y we need to calculate it or not, but y we have already calculated, so we can ignore this, right? So we'll ignore this, and now we'll move on towards this d. Now do you see any problem with this one? Well, definitely we are seeing a problem with this one, and the problem is that over here the dependency is like this, that b has to come before a and a has to come before y in order for us to generate the dependency order. But over here when we started traversing, the actual dependencies we are getting is actually in reverse order. You see that y comes before a and a is coming before b. So one way we can do it is that we can start traversing like this one, that over here we again come to this d. For this d we find a dependency as l. For this l we find a dependency at I. For I we don't find anything, so we'll just put I over here. Then we backtrack, so again we put l over here, and then again we backtrack, and then we will put d over here, and then we come to this t, like this I, this l, and this has already been done, so we ignore that. We come to this t does not have any dependency, we put it there. I has already been processed, and we reach at over here at r. Now this order list we got is actually correct, but in reverse order, because the dependency should be like b a y, and this should be d l I, but over here it's d l I in reverse order, and same goes for b a y. So what we will have to do is when we calculate the answer, we will have to return the reverse of this answer, and that would actually satisfy these dependencies. So that is one way of doing it, right? And there is also another way of doing it, and the better way is that when we are actually creating this hash map, we can actually do something different. Previously in the hash map, what we are doing is that over here we had a key as all the unique characters, and as the value we had these dependencies exactly as they were mentioned, that for this particular b it is dependent on a, for this particular a it is dependent on y. But the thing is that is not true. The actual true thing is that actually this y, the position of y should be dependent on a, that y cannot be present unless there exists an a value before that. If we start, so if we, rather than storing the dependency on value that is taking care of the value that comes after it, if we start taking care in reverse order, so let me show you what I mean by that. So suppose if we have a hash map like this, and over here in the value we actually present at any given value what should be the previous value that has to be present in order for us to reach at that particular value. So what that would do is that if we want to calculate this b, we don't need to basically have any value, right? So over here we will leave this as blank, that for b we don't have any dependency. But for this particular a, we actually have dependency on b, that b has to be there in order for us to process this a. So we will put a dependency over here saying that okay, b needs to be there for us to calculate this value a. Same goes for y, that a needs to be there in order for us to calculate this value y. Again we reach at this d, and for the d we don't have any dependency, so we'll just leave it blank. But for this particular l, again we will have to have a d over here, so we'll put a d over here. For this t we don't have any dependency, so we can leave it blank. For this particular I, we actually have to have an l before that, so we'll put a dependency over here. And for this r we don't have any dependency, so we'll leave it blank, right? So this is the table this is the hash map that we work with. And over here, now let's try to iterate over this hash map. Essentially our aim is to iterate over this entire hash map, identify that at any point if you are inside the DFS function you are not finding the repeated character, so that is item number 1. Second thing to make sure is that you go through all the characters and you start building up the order list. So over here we will get we initially start at b, and at b we don't have any child, so we are good to put b over here. Now next and we can mark that b is already done. Now we are at this a, so for a we need to check that whether b is done or not. B, we check over here, b is already done, so we are good, which means that we can put a over here. So we will put a over here. Again we will mark a as being done. Again we are at this y, we check that okay, y has dependency on a, so we check okay, a is already done, so we can put y over here as well. Now we are at this d, so d does not have any dependency, so we can just simply put d over here and we can just mark this as done. Again from l we check for d, d is already marked, so we put l over here. T does not have any dependence and we mark l, t does not have any dependency, so we mark t is done, we can put it over here. Now this I has dependency on l, we have already marked that it is done, which means we can complete this I as well. And for this particular r, it does not have any dependency, so we can put it over here. Now if you notice this scenario, we are actually fulfilling both of these dependencies. And notice that this b comes before a and comes before y, so we are good with this dependency. This d comes before l and I, so we are also good with the second dependency as well. And this t and r, they were actually separate values, so it doesn't matter wherever we put them, as long as they are there, it fulfills our purpose. And this is the actual solution that we need to take care of, that where initially we will iterate over all the words, we will create all the unique characters. Based on the unique characters we will create the dependency list. Based on the dependency list we can actually create a hash map that we are going to use to traverse as a graph. But the thing is, rather than traversing the original hash map, we can actually create a reverse list of dependencies, and we can iterate over that just once using DFS or BFS, anything, but we are going to use DFS because I want to master DFS for myself, and that would be our solution. So it took me a lot of time to come up with this solution. It took me a lot of time to understand this problem. Okay, let's calculate time and space complexity for this problem. So the time complexity for this one is going to be big O of C, where C is actually total number of characters that are given in this original input words. Because notice that there are three parts of this problem. The first part is that we need to find all the unique characters. Like in order for us to generate all the unique characters, we will have to iterate over all the characters that are given in the original input words. So that is one part. Now second part is that we need to create a dependency, and in order to generate the dependency, again we will have to traverse all the words. And the third part is that we will have to so we are generating some sort of hash map, and inside the hash map we will have to iterate over all the values inside the present hash map. So at any given moment, the maximum work we are doing is iterating over the sum of all the characters that are given inside this words. So that is why that would be the time complexity. And if we want to calculate the space complexity would actually depend on the number of unique characters. So suppose that in English language, the number of unique characters maximum we can have is only 26, right? And we are also told that for this alien language, the maximum number of unique characters we can have is also going to be 26. So space complexity actually has a finite number, and there is only so much it can grow. So we can treat space complexity to be big O of 1 or constant space complexity for this one, even for us to creating this additional hash map. The second thing is that suppose if we want to calculate based on the number of unique characters, there is also one equation where the space complexity would actually be big O of u plus whatever the u square or n, whatever the minimum value of this is. And let me know in the comments if you want me to explain the space complexity in a scenario where the number of unique characters are actually not finite and not 26. Like in this case it's 26, so I will just leave it as it is, but let me know if you want me to explain that. First of all, we are going to create our hash map, and we are going to actually create it outside of this alien order method that is given, because we want to use that hash map to our DFS method as well. So, and as a key we are going to use unique characters, and as a value we are going to use the dependency. So it would be list of characters, and we are going to name it reversed list, because essentially we are just reversing the adjacency list. Also we will create another hash map to essentially store the value of any parameter that we are already currently visiting inside our DFS method. And so we'll need to create an output of strings, so we can create a string builder variable. Now the first thing we need to do is find all the unique letters inside our given word string of words. Now this is done. Now we will have to find all the edges, and we will have to add the reverse edges to our reverse list hash map. Now at any given moment we need to check that whether the word 2 is actually prefix of word 1 or not. If that is the case, we can return false immediately, and we have found a terminating case where the given string of words is not valid. Okay, if that's not the case, we will find the first differing character between two words and add it to our hash map. And notice that we are actually adding the value to the second word's differential character. And the moment we find the first differing character, we can actually break out of that particular word. Now we are going to iterate over the reverse list hash map that we have created, and we are going to run our DFS function. Okay, for all the keys present inside the reverse list hash map, we are going to run the DFS function, and we are also going to check that at any given moment have we receiving the result as false. So we are just going to create a boolean variable result, and now we are going to call the DFS function, and we are going to provide the character inside the reverse list. And at any moment, if we identify that the result is for this result character is actually fault, we will return empty list immediately. Okay, now all we need to do is that once this DFS step runs, we should have our output inside the result. So we will have to check that whether all the unique characters have been taken care of or not. So we are going to check that whether the length of output if that is less than the size of our list, if that is the case, we can return false immediately because we haven't taken care of all the unique values present. And if none of these cases happen, we will return whatever we find inside the output. Now the only thing we need to do is we will have to create the DFS method. Now first of all, we are going to check that whether the current character C we are checking, if we have already visited that or not. If we have already visited that, we are simply going to return false. If that's not the case, which means first we'll add the current character to our scene hash map, and we are going to mark the entry as false, so that way whenever if we encounter the repeated value, it will always return false. Otherwise by default the value would be true. Okay, now for every single character inside the current for the given character, we will iterate over inside the reverse adjacency list, and at any point if we encounter the result false, we will return false immediately. If that is not the case, we will remove the entry from the scene hash map. So we'll set the entry as true, and inside our output string we will append the value. And for that particular character we are going to return true. Okay, so I know this is a very long and too many lines of code. I'm going to put this in the comments. Let's try to run the code. Okay, seems like our solution is working. And also remember, I was talking to you that we will have to take care of all the unique characters. Here let me show you an example. So suppose we only have two characters, H and P. If we are only given input like this, and we know that H comes before P, right, which means that in the result we should be getting HP. So let's see that what, okay, so this is accepted, right? But now let's say that we have additional character HA and PB. Now over here we don't have any mechanism to measure this A and this B, so they become unique characters, right? And now let's try to run the code for this particular test case. So if we do that, you are going to see that A and B would be at weird locations. So over here, see, the important thing is in our output we are maintaining the order for this H and P, and that is what it matters. Like A and B over here in our output is actually behind this HP, while over here the A and B are actually at the beginning, and then there comes HP. So it doesn't matter as long as the order that is given in the input is maintained. And now let's try to submit this code, and oh wow, our solution is actually 99% faster than all the other solutions. And I used lot of help from the solutions tab from this LeetCode Premium, because it took me a lot of time to understand this problem. So I'll be posting this in the comments, you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important LeetCode graph problem, graph valid tree. Basically we are checking that whether the given graph is actually a tree or not. And this question has been asked in a bunch of different top tier companies, companies like LinkedIn, Google, Amazon, Bloomberg, Microsoft and Facebook. So these are my dream companies, so I'm paying my utmost attention. I hope you enjoy the video. Okay, so this is a LeetCode medium problem, and we are given n number of nodes. We are also given a list of edges, and we are told that these edges are actually undirected edges. Now we need to see that whether the given graph is actually a valid tree or not. If it is a valid tree, we'll return true. If it is not a valid tree, we'll return false. And we are also given an example to understand this problem. Like in this example, we are given these 5 nodes and we are given some list of edges. Based on this list of edges, they have shown that this could be a pictorial representation. And over here, they are saying that, yeah, this is a valid tree. So that's why they are returning true. Now the question is, in order to understand this, first of all, we will have to understand that what is the relationship between any graph and a tree. What is the difference between a graph and tree, and how can from the given input we can identify that, okay, this is a valid tree or not, right? That every single tree is also a graph, but that is not the case for every single graph, that it will always be a tree. Because if I put it in Venn diagram, essentially graph is actually a superset, and tree is just one of its subset. So this can be a tree, and this is a graph. There are a lot of real life cases to understand that as well. Like the person who got slapped by Will Smith is always going to be a human, but not every single human has been slapped by Will Smith. It is something in that kind of relationship, right? Now the thing is, what are the differences between a graph and a tree? That inside the tree, all the components are connected, or all the nodes are connected. There is no restriction for graph that all the nodes should be connected. And the second difference is, inside any tree, we will never encounter any loops. So we can just say no loops, while inside the graph there can be loops. Let's try to understand this with some examples. Is this a valid tree? Actually, yes, this is a valid tree, because notice over here that from one node, like every single nodes are connected with each other, and we do not find any single loops. But the thing is, say for example, in this case, if I had an additional edge, something like this, I can clearly see that there exists a loop between these 4 nodes. And because we have identified a loop, we can clearly say that this is a graph, but this is not a tree. Now let's take another example. Now this is a valid tree. Like all the nodes, they satisfy these 2 properties, that they are connected and there are no loops. The same graph, if I had some components like this, some additional nodes, though they are not connected with all the nodes, they are connected with each other, or there are some isolated nodes, something like this. If this is the case, this will always be true, that okay, this is a graph. We can put it in the category of graph, but this will not be a tree. And in this case, we will need to return false. Now, before we move on towards solution, I just have a simple request. If you see, a lot of people, they watch my content, but they are actually not subscribed to my channel. It takes me a lot of time and a lot of effort to make these kind of videos, and I would really appreciate if you can just show your support and subscribe the channel. Like, now this problem actually can be solved in so many different ways, and I'm going to show you a few different ways on how we can do things. Now the question is, what we need to find basically we need to find that whatever this given input is this a valid tree or not. In order to find that whether it's a valid tree or not, we need to check 2 things: whether all the nodes are connected, and if there are any loops or not, right? So what I'm suggesting is that we break this problem in 2 parts. In the first part, we check that what could be the different ways we can see that whether these nodes they are connected or not. If they are all connected, we are good, and if they are not connected, we can return false immediately, that this is not a valid tree. And once that is done, we will find all the ways on which we can identify that whether there are any loops or not, right? So first, let's go with the first approach. Now our aim is to check that whether all the nodes are connected or not. What could be the different things we can do over here? In order to check that, essentially what we will need to do is we'll have to traverse over whatever this given input graph is. Now traversing over this given input graph based on the structure we are currently given in the input is going to be a little bit tricky, based using this number of nodes and edges. So the question is, like, first thing we need to do is we will need to convert this given input in either adjacency list or adjacency matrix. either of them can be used and it will work perfectly fine. But then in this case, I will suggest to use adjacency list. We only use adjacency matrix when there are too many edges. We don't have any clear indication in this case that there would be too many edges, and we would try to use an adjacency list, right? So now we are trying to check that whether all the nodes are connected or not, and we have already created our adjacency list. Now what I'm suggesting is that through this adjacency list, we know that we would be able to iterate over this given input. And through this given input, what we do is we create a hash set. Inside the hash set, initially it would be empty. Whenever we are at any point iterating over any single node inside this given hash set, we will check that whether that particular node already exists in the hash set or not. If it does not exist, we will add a new entry inside the hash set. And at the end, once we have traversed all the values inside the given input through this adjacency list, what we are going to do is we are going to check that what is the total size of hash set and what is the total number of n given. If both are same, we can conclude that from any single point we are able to reach to all the other elements. And because we were able to reach to all the other elements, all the elements are connected, and we at least satisfy one condition. So let's see that how it would work. Suppose in our adjacency list, we start traversing through this position number 1, right? So initially we check that whether this value number 1 exists in the hash set or not. It does not exist. So we'll add an entry over here that, okay, value number 1. Now through this value number 1, we can traverse in two directions. We can either traverse to the neighbor on the right or neighbor on the left. So let's say that we go to this node number 0. Again, we add 0. From the 0, we go to node number 2. Again, we come to 2. Now from this 2, we can't go any way forward, right? But the thing is, we still need to go back. We'll need to do backtrack. We'll go back to 1. Again, through 1, we will go back to 3. Now at this 3, this is not added, so we add it over here. From this 3, we will go to 4. So we will add 4 over here. From this 4, again we will do a backtrack, and we would come back at 3, and then we will come to 5, and then we will add 5 over here. Now at the end of this hash set, we are able to iterate over all the elements inside the given input, right? And we check that what would be the size of this hash set. So size of this hash set would be 6. And what is the given n? So n is also 6, which means in this case, we are at least able to conclude that this given hash set is actually satisfying our condition, and inside this given graph, all the nodes are connected. So we are good. Now suppose in this case, if we had another node, something like this, and this was not connected to any of them, basically this would not have been entered inside our hash set, and our n in this case would have actually been 7 rather than 6. So we can clearly see that if our size of our hash set is going to be lesser than whatever the number of n we have, if that was the case, we could have written false immediately, because we found that there exists some not connected component, and which was not the case in this case. So this is one of the very good approaches to identify that whether the graph is connected or not. Okay, now we have taken care of the first part, and now we need to take care of the second part, that we need to check that whether in the given graph does there exist a cycle or not. So first thing that comes to our mind is that why don't we use the visited hash set that we have already created. And in that visited hash set, what we are going to do is at any point in time, we are going to start exploring from one of the node in the given input graph. From that node, we are not going to stop exploring till we exhaust all the neighbors of this particular graph. And at every single time we are planning to come to next element, we would first check that whether that element exists in the visited hash set or not. If it exists, then we would consider that there exists a loop, and we would break out of it. If it does not exist, we would add that entry over here. So first we will start traversing this value number 0. So it does not exist in visited, so we will add an entry over here. From this 0, we will start exploring its neighbor. So one of its neighbor is this value number 1. And remember that we are going in depth first search, so we will not stop until we exhaust all the possibility in one direction before going to the other neighbor. We could do it breadth first search way as well. It's up to us. Now From this one, again depth first search, we see its neighbor, that there is a neighbor 2, so we add an entry over here because it does not exist. Now remember that this is actually an undirected edge. So what does an undirected edge means? Undirected edge means that from 0 we have an edge to go towards 1, and from 1 we have an edge to go towards 0. Same goes from 1, that we have an edge to go towards 2, and from 2 we have an edge to go towards 1, and same goes from 2, that we can go to 0 and we can come back. Now over here from this position number 2, because we have an edge that goes to 0, we can consider that 0 is also a neighbor of 2. In this case, from this 2 we will try to go to the 0, and the moment we try to go to the 0, we will see that okay, it has already been visited, it is part of this hash set. So we would say that okay, there exists a cycle, and we are pretty happy with ourselves that hey, we have identified a cycle and now we are done with our case. But the thing is, this is actually a wrong approach, and the reason why it is a wrong approach, it is wrong approach because there exists this undirected edge. And let me show you by an example that what could be the problems if we keep using this visited hash set only, and how can we find false positives. So suppose we are given an example like this, that 0 calls 1 and 2, and that's it. This is the input we are given, right? And now we don't have any entry inside our hash map. Now the thing is, all the edges are undirected edges. Now because they are undirected edges, we can represent them in different manner. So let's represent them in slightly different manner. So from 0 we have an edge that goes towards 1, from 1 we have an edge that goes to 0, same goes from 0 to 2, and 2 to 0. Now initially we start traversing from this 0. Now we have our algorithm that initially we are going to add the entry to visited hash set. So 0 does not exist, so we add the entry towards our visited hash set. Now from the 0 we need to check all of its neighbor before we move on to some other node. Now from this 0, first of all, let's say that we go down this path and we check its neighbor 2. Because there exists an edge like this, we are able to check its neighbor, right? So we are at this position number 2. Now at this position number 2, we don't have an entry in the visited hash set, so we enter an entry over here that this is 2. Now from this 2, again we will need to repeat the same process, that we will need to check for all the neighbors or all the edges that this 2 can point to. Now it does not have any edges that go further, but it has an edge that goes back to 0. Now the thing is, in this case, again we will use our same logic. So from this 2 we can still go to 0. So we will check that whether we have visited this element 0 or not, and over here we find that hey, we have already visited this element 0, which means by our logic that we were previously trying to impose, we could have said that okay, we have found a cycle that looks like 0 to 2 and 2 to back to 0, and we in this case say that hey, we have found a cycle and this is not a tree and we will need to return false and blah blah blah. The thing is, this is actually not the case, and why it's not the case is because of this correlation of having an undirected edge that is causing all this problem, which means that we cannot rely only on having a visited hash set. If we do that, then essentially we are not going to be able to find an answer, because in this case we know that from there does not exist an edge, and from this 2 we are coming back to 0 only because there exists an undirected edge from this 2 to 0, and that's why we can consider this 0 to be 2's neighbor. But in reality this 0 is actually parent of this child 1 and 2. So if that's the case, why are we still doing things like this? What could be a better approach we can use to find that what would be the solution to detect these cycles? There are a couple of different ways where you can tackle this problem. One way to tackle this problem is that initially, remember, the only reason we are causing this problem is because there exists an undirected edge, which means that there exist 2 directed edges from any 2 nodes. So what we can do is we can put a condition that from any point, if we travel from this 1 to is 0 or 2, if we are able to travel in one direction, we would get rid of the remaining edge. And let's see that how it would work. So what I'm proposing is that initially we are at this 0th position. So we check in our visited hash set, we don't have any entry, so we add an entry over here that okay, we are at the 0th position. Now from the 0, first let's say we travel to 1. which means that now we have traveled from 0 to 1 in this direction. So our aim is that we get rid of this reverse edge in our adjacency list. So if we get rid of that, now we are at this position number 1. At this position number 1, again we add an entry over here in our visited hash set. Now from this position number 1, what we have to do is we will have to check that what are all the neighbors that we can travel to, or all the children we can travel to. But this one does not have any neighbor or children, so which means we don't have to worry about anything. So over here we can say that okay, from this one we can't go anywhere, but thing is there still exists some nodes that we haven't traveled to, and we are using either BFS or DFS in any manner to traverse over entire graph, right? So which means that we will have to do a backtrack. So now from this one we do a backtrack. Now again we end up at this 0. But thing is, in this scenario, remember, we are not ending up at this 0 because from 1 there existed an edge like this where we consider 0 to be 1's neighbor. We are coming back to this 1 because we are using backtracking through any BFS or DFS algorithm. We can implement this recursively or iteratively, doesn't matter. In any scenario we will have to iterate over all the nodes that are present inside the given graph, and since we haven't traveled all the nodes, that's why we are coming back to the 0. So again this would be a new entry in the visited hash set. So again we come back at the 0, and this 0 we check that okay, we have already explored one of the neighbor of the 0, but we still have to explore another neighbor. So again we repeat the same process. From the 0 we explored another neighbor of 0, we come back at 2, and immediately we get rid of this this edge that was coming back to it, and then we add an entry over here that okay, we are at this position number 2. Now from this 2, again we don't have any more neighbors to go to, so now we have explored all the neighbors of 1, so we can mark 1 as being done. We have explored all the neighbors of 2, so we can mark 2 as being done. And now we come back at the 0, and we can mark 0 as being done because we have explored all the neighbors of 0 possible as well. And in any scenario we did not find any single loop because we did not find repeated value inside our visited hash set. So we can determine that there does not exist a cycle, and which means in this case we can return true because there are no cycles. So we can say that there is no loop for this one. And the only reason we are able to come up to this conclusion is because at every single position we were removing the edge where in one direction we have already traveled. So that is one way to take care of this problem, and the solution would work as expected as well, right? Now the thing is, there could be another solution where we can use the little bit different logic, little bit different data structure, and we can do things in better manner. And let's see that what would be that approach. So the second approach is that rather than using this visited hash set, we don't need to do anything with this visited hash set. Let it be used for the purpose of counting that whether all the elements are connected components or not. What I'm proposing is that we created another data structure, a hash map, and in this hash map, what we plan to do is we as a key we have parent, and as a child we as a value we have the value of its children. Now let's see that how can we use this combination to do things a little bit differently. Also over here, let's say that we are given a graph like this, that 0 1 2 3, something like this, right? So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and now we have this 3 connected back to this 1 as well, which means that there exists a cycle over here. Now because these are undirected edges, which means that they are bi-directional edges as well. So from this 0 we can go to 1, from this 1 we can go back to 0, and blah 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 whatnot. So initially let's say that we are at the 0th position. From the 0th position we start exploring its neighbor or children or whatever you want to call. So the moment from the 0 we are able to reach to this one, we would add an entry over here in this hash map, and the entry we are going to make is that 0 is actually a parent in this case, and one of the children that we could find for this 0 is actually node number 1. So node number 1 is the children of 0, and just stay with me that why we are using this approach. Now again from this node number 1 we need to explore its neighbors, right? So what are the neighbors of this node number 1? We can explore neighbors based on the number of edges that goes out from this node number 1. So from this node number 1 we actually have two edges that goes out. First edge is that from this node number 1 we can go to node number 2. Now we check in this hash map that does node number 1 exist. Node number 1 does not exist as a key, so we add an entry over here. So we say that okay, parent is node number 1, and from this node number 1 we can actually travel to node number 2. So we are good with that. Now again from this node number 1 we still have possibility that we can go back to this node number 0. So again we check in this hash map, okay, that whether there exists an entry for this node number 0 that we are trying to reach. Remember this very importantly. We will check that whether this node number 0 that we are trying to reach from this node number 1, does that exist in the hash map or not. Okay, so 0 exists in this hash map. Again we check that from this 1 we are trying to reach to this 0, is this one of the children of this node 0 or not. In this case, yes, 1 is the children of node number 0. If that is the case, we can identify that this connection from 1 to 0 is actually not a cycle, it's just a trivial loop, and that is being caused because there exists an undirectional edge on both the sides. So that's why we will ignore this case, we will ignore this connection. We are not removing the edge. Again, remember, we are not removing the edge, we are just ignoring this case because in the hash map we are able to find that okay, this 0 to 1 connection is actually just a trivial cycle, and we move on with our life. So from this 1, again, since we have reached to this 2, right, and 2 is not existing, and 2 is one of the children of 1. Now again we are at this position number 2. Now again from this position number 2, what are the different ways we can travel? We can either go back to 1 or we can go to 3. Let's say that we go to 3 first. So we check that whether 3 exists inside the hash map. 3 does not exist, which means we can create an entry that where 2 is a parent and 3 is a child. We are good with this so far. Now again from this 2, when we try to check that from 2 we are trying to go back to 1, is that a cycle? So first we check that whether this 1 exists in the hash map or not. So 1 exists in the hash map over here, and 2 is one of its children. So because 2 is one of its children, we are going to ignore this case, and we are going to and because we are ignoring this particular, we are just going to move on with our lives. Now we are at this position number 3. From this 3 we will check that okay, what are the different places we can travel back to. So from this 3 we see that okay, one edge that goes to 1, one edge that goes to 2. First of all, let's explore this edge from 3 to 2. So over here we will check that we are trying to reach to this node number 2. So 2 already exists and 3 is one of its children, which means we are going to ignore this edge, so we don't have to worry about anything. Now again from this 3 we check for this value number 1. So okay, from this 3 we try to see that whether we are able to reach to node number 1. Node number 1 has already been visited inside the hash map, and that's why we are able to determine that there exists a loop inside over here, from where we are actually going back to one of the places that was actually not that is already been visited inside our hash map. And this hash map acts as both. It acts as a visited hash set that we were planning to use, and also it acts as a way for us to determining that whether we are detecting the correct cycles or we are detecting the trivial cycles between the unidirectional edges. And this would be a way on how we can check the cycles, which means that the combination of this, using this hash map to identify that whether cycle exists or not, and using this visited node and iterating over using BFS or DFS inside our graph, original graph, using these two data structures, we can actually get rid of both of our cases where we need to check that whether the graph is connected, and we need to check that whether the graph contains any cycles or not. And because we are able to do both of these things, at the end, if we are able to reach to end node, we will return true. If we are not able to reach to end node, we can return false. And this solution actually works perfectly fine. There are no issues with this solution. It is a very elegant solution. If you tell it in any interview, they are going to be very impressed with the depth and breadth of your thinking capabilities. What are the space and time complexity over here, and can we do something better? So let's first try to determine that. So space complexity, in this case, we know that we will have to use the hash map, and we will have to use the visited array as well. Inside the hash map, we are going to iterate over all the nodes plus all the edges, which means that over here the space complexity would be big O of V plus E, because we are iterating over all the vertices and all the edges. The time complexity in this case would also be big O of v plus e, because we will have to iterate over every single node and every single edge multiple times in order to come to this solution. But the thing is, we are not doing loop inside loop work, so which means we are not doing repetitive work at any given moment. Okay, after such a long explanation, let's see that there be a better approach. And yes, there is actually a very elegant, very beautiful solution where actually we don't even have to go through all of these mess to detect that whether cycles exist or not. In order to do that, actually we need a higher knowledge of graph theory. What do I mean by that? Okay, at any given moment, suppose we are given a graph like this, that 0 1 2 3 4. Suppose we are given a graph like this, right? Now if we want to identify that whether this is a tree or not, like in this case we can clearly see that yeah, this is a tree, there is a very legitimate scenario, there are no cycles, all the nodes are connected and blah 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 whatnot, everything is good with this, right? Can you notice an important property over here? The important property that I'm talking about is, if you count that what are the number of nodes and what are the number of edges, does there exist a correlation? Yes, actually there exists a correlation, and the correlation is that suppose we are given the number of nodes equal to n, and if we are given the edges that are n minus 1, and we determine that all nodes are connected. If we determine that all nodes are connected, because remember, in our solution when we are trying to finding that whether the nodes are connected or not is much simpler. We simply need to use a hash set, we need to iterate over whatever the given input we have, and basically we can determine that okay, whether the nodes are connected or not. But checking for the cycle is slightly more complicated, actually not slightly, much more complicated, because either we have two options and both options require us modifying a lot of things or managing a bunch of different data structures. Either we can choose to remove the edges like this, or we can choose to create a hash set like this. In both the cases we are actually doing a lot of work. So what if we actually don't need to encounter that whether we need to find the cycles or not? If we only encounter that whether the given nodes are connected or not, if that is true, and at any given moment we identify that okay, all the nodes are connected, and then we identify this property that whether the number of nodes that are given and number of edges that are given, if there is the difference between them is only 1, if that is the case, then the given graph will always be a tree. Let's see in this scenario we can identify that okay, from this 0 all the nodes are connected, that this 1 2 3 and this 4 we are able to connect to all of them, right? What is the number of nodes? So number of nodes in this scenario is actually 5. This 1 2 3 4 5. Now let's see that what are the number of edges. So if we calculate the number of edges, the number of edges is okay, this is one edge, this is second edge, this is third edge, and this is fourth edge. There are only 4 edges that are possible. If we have any more edges, then for sure there would be a loop. Because remember, where would you add an edge in this scenario? You can add an edge over here, okay, that creates a loop. Let's say that you don't add an edge over here. Suppose you add an edge over here, again it creates a loop. Well, you don't even add an edge over here, you add an edge like this. So again this creates a loop like this. Eventually, as long as the difference between the number of nodes and number of edges is actually not exactly 1, and if the number of nodes are one number higher than whatever the number of total edges are given, if that is the case, and we determine that all the nodes are connected, then we can clearly say that okay, everything is good with our life and we don't have to worry about anything. Why we need to check that whether all the nodes are connected or not? The only reason we need to check if all the nodes are connected or not is, suppose we are given a scenario like this, that we are given these three nodes. Suppose we are given these 4 nodes, right? And in these 4 nodes, so remember our equation is that number of nodes and edges. So if nodes are 4 and if edges are 3, so we can say that okay, everything is good with our life. In this case the number of node is 0 1 2 3. Okay, so total 4 nodes, we are good. Number of edges 1 2 3. So this is also good. The thing is, over here you can see that there exists a cycle over here between these three edges. And why there exists a cycle? Because this particular node is not connected. So always at any case we will have to check that whether all the nodes are connected or not. And once we identify that all the nodes are connected, we are good, and then we can just wrap up our solution. So using this solution, actually everything becomes so smooth that if we calculate the time and space complexity, the time complexity in this case is actually big O of n, because we only need to iterate over the given number of nodes, and where n defines the number of nodes. If we calculate the space complexity, the space complexity is also big O of n, because we only need to maintain a hash set to take care of with all the number of connected edges. So once we find out that what are the number of connected, if all the elements are connected, we can immediately identify that whether this given graph is a tree or not. So let's move on towards coding now. First of all, we are going to check that whether the given number of edges, if its length is one less than the number of nodes or not. If that is not the case, we can return false immediately. So, and if that doesn't happen, we will have to make an adjacency list. So we will create an adjacency list, so it becomes easier for us to iterate over the given input array. So for all the given n, we are going to treat them as vertices, and all the values that are provided in the edges, we are going to treat them as edges basically. Notice over here that for every single edge, we are actually adding 2 entries inside our adjacency list, and that is because the given edges are actually undirected. So that's why we will have to add an edge for both the nodes. So if there is an edge between 0 to 1, so we will have to create 2 edges, and those 2 edges would be 0 to 1, and from node 1 to 0. So that is what we are doing by this second for loop. Okay, now we will start iterating over the given graph inside the adjacency list. And I want to learn that how to iterate over the graph using stacks. So I'm going to do it using stacks, and I will be doing iterative depth first search. So first I'll initialize a stack of integer values and just name it as stack. And we will also have to create a hash set of integers called visited. Inside our stack, we will add the first entry. So we will add the node 0. And inside our hash map visited, we will mark the first node as visited. We will pop the first node that is inside our stack, and then we will start iterating over its neighbors. And we'll see that if that neighbor has already been visited, then we will simply ignore that case. If that is not the case, we will start iterating, we'll start adding those neighbors to our stack as well. And we will also add that neighbor to our visited hash map as well. It would be neighbor, not node. Okay, and after this loop ends, we only need to check that what is the size of our hash set. So if, or else we will return false. And let's try to run the code. Okay, seems like our solution is working. Let's try to submit this code. The problem is called number of connected components in an undirected graph. And if we see some of the popular companies who have already asked this question, there are companies like TikTok, Amazon, Google, Facebook, LinkedIn, Microsoft, DoorDash, and Twitter. So this problem has been really popular amongst topmost companies. And let's see that what the problem statement is trying to convey. Basically, this is a LeetCode medium problem and also very well-liked problem. It says that we have a graph of n nodes that we are already given, and we are basically given the edges that defines that there is a connection existing between those two nodes for any given graph. Now based on that, we need to indicate that how many number of connected components are present inside the graph. So let's try to understand this with an example. In this case, currently we have 5 nodes. So basically we are given an n is equal to 5 as the number that defines that there are 5 nodes. We are also given these edges. So we would have given 3 entries, and the first entry is going to be 1 to 2, second entry is going to be 1 to 3, and third entry is going to be 4 to 5. Now based on these two items, we need to define that how many number of connected components that exist, which in this case we can see that this is the first connected component because these 3 nodes are connected with each other, and same way this is the second connected components. So in this example, for this given input, we can define that there exist 2 connected components and we need to return 2 as the answer. So this is the whole ask of the problem. Let's try to understand this with one more example. Suppose in this case, currently we are given n is equal to 7 and we are given all of these different edges. Now in this example, we can clearly see that there exist 4 different connected components, and those 4 components are these, that this is the first one, this is the second one, this is the third one, and though this 7 is not connected with any other node, still this is a connected component in itself because it's connected with itself. So in this case, in total, since we have 4 connected components, we need to return 4 as the answer. Now let's see that what is going to be the strategy to solve this problem. Suppose we take the same example as the input and we will try to see that what should be the answer. Now again, remember, we are given 2 things. First, we are given n is equal to 7, so that we know for sure there exist 7 nodes, and we are given all of these 5 edges. Now based on these number of nodes and edges, we can clearly do one simple thing, and that is to treat this as a graph problem, because that what it is. Basically we know that a graph is comprised of 2 items. First one is a node and second one is an edge, and which we are just told in plain English that these are the 2 entities we are given, so we are going to treat this one as a graph. Now the aim is to find connected components, which means from any single edge or any single node, we will need to define that how many other nodes that particular node is connected with. And if we keep on repeating the same process, and the moment we find the connected nodes, we can eliminate all of those nodes, so and repeat the process for all the 7 nodes that are given, we would be able to find the number of connected components quite easily. And the technique we are going to use over here is the one of the most popular technique in the entire coding industry, and that is called breadth first search. And how we are going to use BFS? Well, we already know that in order to use BFS, we will have to use queue, and we will also have to use number of visited nodes that we have already visited. So using these 2 items, we are going to make our lives so much easier, and let me just walk you through the solution. First thing we are going to do is we are going to we can start from any node, because this is a graph. There is no particular definition that we need to start from here or we need to start from here. Say for simplicity, we start from this node number 0. So we are going to have our queue. Now inside our queue, currently we don't have any elements, and we also have our visited hash set. We can also use visited array. I'm just giving you example of visited hash set. Either way, we are going to have a mechanism to keep track of all the numbers or all the nodes that we have visited so far. So this is our visited hash set, and this one is our queue. Okay. Now first we start with node number 0. Now for node number 0, we are going to mark this one as 0. So we are going to enqueue with 0. Now we are also going to mark 0 as visited. Okay. And we are also going to have one more number that is called the number of connected components. So let me just mark this one as counter. Okay. and currently the initial counter value is going to be 0. But since we found one node, we know for sure that there exists at least one connected component, because it could be connected to itself. So in that case, we are going to increase the number by 1. Okay. Now for this particular 0, we are going to run BFS, and by running BFS, what we would be able to do is that we would be able to go through all the neighbors that this 0 is connected with, and then mark all of them in the visited hash set. So even in the future, for this n is equal to 7, if we come back to the same node, if that node has already been visited, we will just simply skip over it. So let's just do that. Now for this 0, it has two neighbors. First neighbor is neighbor 2 and neighbor 1. Currently both are not visited, so let's just add entry 0, 1 and 2 over here, and then we will mark 1 and 2 inside our queue, because we need to do something with that. Currently the count is still going to be 1 because all the nodes are connected. Now we pop 0 out and we do the same process with 1. Currently for the value number 1, 1 is also visited. So since 1 is already been visited, we do not need to do anything with 1, and we can simply pop that one out. Again, 2 is also visited, so we do not need to do anything, and we can pop it out. Now after iterating, or after doing the BFS starting with the node 0, we have simply eliminated node 2, node 1 and node 0 by itself, and so far the count has been 1, and we have all of these 3 nodes in our visited hash set. But we know that there are still 7 nodes that we have to take care of. So we are going to iteratively go over every single one of them. Initially we started with 0, so we got rid of it. Let's just start with 1. Again for 1, since 1 has already been visited, we do not need to increase the counter and move on to the next value. Again 2 has also been visited, so we do not need to increase the counter and move on to the next value. So all of these, this entire connected component has been taken care of. Moving on to the next value, starting at position number 3. Since 3 has not been visited, adding 3 over here, adding 3 in the queue as well, going through all the neighbors of 3. Currently 3 only has one neighbor, and that is value number 5. 5 is not being visited, and also since we find a new element 3, I forgot to add the increment the count. So now the number of connected components we have found so far is going to be 2. I forgot that, but this is important. Now going back, the currently 3 is connected with 5. 5 has not been visited, marking 5 as visited, at the same time adding 5 inside our queue to visit further neighbors of 5. Now 3 does not have any more neighbors, which means we can get 3 out or dequeue 3, and then we are going to have value number 5 remaining. 5 has one neighbor, that is 3, but since 3 has already been visited, we cannot do anything with that, so we are also going to get rid of 5, and 5 has also been taken out. This means that currently we do not have any elements inside our BFS function. Now moving on, currently we went through 0, 1, 2 and 3. Now we need to go through value number 4, because there are 7 elements inside our given input. For even again repeating the same process for value number 4, currently 4 has not been visited, so we will mark value number 4 as visited. At the same time, we are going to put 4 inside our queue. We are going to go through the neighbor of 4 current, and we are also going to increase the count. I always forget to increase the count, which is the most popular thing, that which is the most important thing asked in this problem. But anyways, now going back for value number 6, it has not been visited, so we are going to add value number 6 over here, at the same time add value number 6 over here. Now we iterated over all the neighbors of 4, so we are going to dequeue 4. After dequeuing, currently there is only element number 6 staying in. 6 currently has one neighbor, that is value number 4, but since 4 has already been visited, we do not need to add it to our queue, and then eventually we would pop out 6 as well. Now what we have done is that currently, in order to find these 3 connected components, we already visited nodes 0, 1, 2, 3, 4, 5 and 6, and all of these nodes are visited. Now in the end, we are going to be at the position number 7. Since for position number 7, this node has not been visited, which means we need to increase the counter. So currently the counter is going to be of value number 4. Now we are going to add 7 to our list of visited nodes, and also we are going to mark 7 inside our queue. Since 7 does not have any neighbors, which means we can pop 7 out immediately, and now our queue is empty. We have already iterated over all the number of 7 nodes that were given as the input, and we are basically done with the problem. So in the end, whatever the value that has been stored inside this count variable is the answer we need to return. So simply at the end, we can return that there are 4 connected components in this problem, and this is the complete solution. Now if you see how beautifully we were able to come up with the solution, and in this case, if you see time and space complexity, the time complexity is going to be big O of v plus e, where v defines the vertices or nodes, and the e defines edges, because that is the time complexity to run the bfs function and go over the entire given input array. So this time complexity is pretty good. If we see space complexity, now space complexity is also going to be big O of v, because we are using the additional data structure of q and also a hash set or array. There are two ways to do it. I typically like to use hash set, but you can also use an array as well. Both would work equally fine. In either case, this is a very good time and space complexity. And remember, one of the most important concept is, inside the graph theory, the breadth first search allowed us to solve this problem smoothly in a beautiful manner. Here is the coding solution for number of connected components in an undirected graph, where first of all we are given in the input the value n, and we are also given a 2 by 2 array called edges. So first thing we are going to do is create an adjacency list and to create a graph like structure. So this is going to allow us to iterate over graph in a much easier fashion, which this process is doing, where we are running across every single edge and every single node and plotting them on the graph. After that, we are going to have our boolean array called visited, and we are also going to have a value called count that initially we are going to set it up as 0. We are going to run our for loop starting from value 0 to the total number of n that is given in the input. And then inside the for loop, first thing we are going to check is that the current ith position, if that is not visited, then we are going to call our bfs function, and at the same time we are going to note it as the new connected component found, and we are going to increment the number of count. Now let's see that what is going to happen in our helper method bfs, where we are taking a graph as the input. We are also taking the number of nodes that have been visited so far, and we are also using the starting pointer from which we are entering inside this given graph. So first of all, we are going to initialize our cube. We are also going to have a visited array that we are going to mark as true for the current node that we are visited. And while there are no entries inside the cube, first of all, we are going to pop the last added element inside the cube, visit every single neighbor of that node, and for all the neighbors that has not been visited, we are going to mark them as visited, and we are going to add it to our existing queue. And by doing this operation, we would be simply running through every single connected component. So suppose here I give you like 0 as the input, then through this bfs method, 0, 1 and 2, all three nodes would be marked visited because they all are connected. And this is what this operation is doing. And in the end, after this for loop ends in our main method, we simply need to return the count that we have found that would allow us to find the number of connected components. Let's try to run this code. And our solution works perfectly fine. Let's submit the code. And our code runs decently efficiently. And don't worry about that you are not being able to see the code. I'm going to put this code inside the GitHub, so you would be able to find it quite easily from there.